presenter to provide us about what you presented here. And we want that you touch upon the current status of what you presented, the best practices, challenges you encountered, and recommendations based upon your experiences. Now, it could be that some of those apply more. You can say whatever you want us to include in this final document. And therefore, we have created a Google Drive. I will send a mail with the link to this drive during the meeting today, so you will have it. Because the idea is that maybe you could already write up your text during the meeting. Then the deadline for this would be the 31st of August, but it's feasible to do it maybe while we're here together. The idea is that the text is about 2,000 characters, but it's not that strict. That's just about 1 to 2 paragraphs. And then we'll also have a table online in which you can add online resources that you might have for teaching with robotic telescopes that might be useful for anyone who will consult the proceedings. So we'll collect this and publish that as well. So that's the idea. Are there any suggestions or thoughts about this format of proceedings? Yeah. Yeah. Well, what we want to do is to have everyone who presented here mentioned in the document so that you have some kind of proof that you were here and did something. That's our idea, to publish a list at the end of the paper with all the contributors. Yeah. So if your collaborators are co-authors, then they will be on there. Yeah. Okay. Any other questions? Yes.
Good morning, everyone. Maybe just a reminder, if you want to speak from the audience, use the microphone. There are people online who are listening in. If you don't speak with microphone, they wouldn't hear you.
Yeah. Thank you for
My
that.
question is about just text. Are we allowed to also send you pictures of things we would want to
That's a
appear?
good point, indeed. We will have some pictures in the document, but we only have 50 pages. So if you have pictures that are relevant, please share them. And then we will have to make a selection. And of course, we will share the document that we compose. So we have a couple of co-editors on this. The people from the OC will help. If anyone is a candidate for helping to make this text, you're very welcome to join. And then we'll select images that go well. An idea is also to create a map with all the locations that we have anno 2024, because it might be an interesting document to look at in 10 years' time, see how things have evolved. Yeah. Any other questions? Yeah. No? Hyperlinks in the text? Yeah, I guess we'll do that because PDFs can be, yeah, can have those. Okay, so we can have hyperlinks in those texts. Okay, then we will move on. I pass it on to the chair again. Thank you.
Thank you, Catherine, for the guidance on the proceedings. Please let's take this seriously because we have a very strict deadline from the IAU. The proceedings must be published on the 4th of November. So all work must be done well in advance, hence the early deadline of 31st August. Let's try our best to do that. If we fail, give other people a chance to write a full paper. Thank you, Catherine. So we will start with, maybe you're wondering who's talking. My name is Prosper Simpemba. I'm part of the Scientific Organizing Committee and chairing this session. So we also welcome the people that are online. I'll request if any one of you is online and you notice someone who's online wants to ask a question, please, you can hint to me. We'll go straight to the talks. We'll start with the invited talk on Global Sky Partners, creating an equitable, scalable, and sustainable education program with robotic telescopes. by Dr. Edward Gomez. Dr. Gomez is the Education Director for Las Cumbres Observatory. Welcome, Edward.
Well, thank you. It's very rare to have applause before you've spoken. It's a real pleasure to be here amongst many of you who I consider friends who I've worked with for many years. And thank you for giving me the opportunity to talk about the Global Sky Partners program. So I work for Las Cumbres Observatory, and we have a global telescope network. We have 25 telescopes at 7 astronomical sites around the world in 3 different classes: 2-meter telescopes, 40-centimeter telescopes, and 1-meter telescopes. And the 10 40-centimeter class telescopes are our education network. So they are devoted to educational projects and educational use. So here we are. There's pictures of the 2 meters, the 13 1 meters, and there are 40 centimeters there. They are plane wave delta rho telescopes, but we designed the mounts here so that they would last for a very long time. We designed all of the 1 meters and the 2 meters as well. We've been operating these telescopes for quite some time now. But back in 2014, when we started to deploy these, I wanted to, as everybody does when you have robotic telescopes and you want to have an education project, you think about the things that you could do. What communities could you engage with? And it wasn't really until 2017 that the idea of actually not doing it as an in-house project, of doing it as an external project came. Here are two shots of the telescope, so you can see the work that went into creating this customized equatorial mount here. So there are 10 of these telescopes in operation. So we came up with the idea of the Global Sky Partners. So instead of running all of these projects in-house, we opened up our telescopes to groups and organizations around the world who had ideas and who had maybe already had educational programs that used robotic telescopes, or maybe they wanted to use robotic telescopes. But we saw that this was an extremely valuable resource. And we also saw that if we opened this up to Western universities, to amateur astronomers, all of the time on those 10 telescopes would be gone straight away. And we can do the most good if we provided these telescopes to groups that wouldn't have this opportunity normally. And so that's why, to become a partner, we have preferential treatment to projects that target underserved and underrepresented communities. We'd ideally like these projects to be innovative. Our telescopes, the 10 telescopes, are not individually operated. They are operated using a common user interface. So you don't pick a telescope to observe on. You say, I want to observe this phenomenon, this object, and it has to be under these constraints during this time, using these filters. And so you can do a lot of innovation with that. Fundamentally, though, these projects have to be educational, and I'm really very strict about that. If a scientist tries to sneak in a science project using this call for proposals, then they give them pretty short shrift by me. And fundamentally, it's an open call. Anybody can apply. And really, the criteria are that you will support your audience. You have a well-defined audience. You have a well-defined education plan, and that you are going to support them. We only refuse people not because of the time budget, but if they're a science project and trying to sneak it in, or if we think that the person doing the project the project won't succeed. And in those situations, I mentor the people so that I give them a small amount of time so that they can test their ideas out, and then they can have a successful proposal the next time. Yeah. So we're currently running this program with 41 partners. So these are organizations and groups around the world, and they annually use about 1,200 hours. And that's not a limit, actually. That's just the amount of time that they use. We really cap the amount of time that's used. The 41 partners are a huge mixture of different types of projects, from citizen science projects where people take observations and then scientists assist the people to analyze that data, teacher training programs, observing campaigns, student research, and artistic and inclusive outreach programs. We had some programs which sonified variable star light curves. I'm not going to talk about any of the partners actually, because we have so many of them speaking, but I'm just going to highlight some of the achievements of the program as a whole. Through this program, around 60,000 people a year have some impact from using our robotic telescopes. That's either through direct use or direct engagement with one of our partners, or as an indirect, because their partner was targeting a teacher and the teacher has a class of students that then use this program. This is far more people than I could ever hope to engage with on my own. And this is a number. It's not showing any depth of the engagement there, but it's many more people than I could have hoped that could have been involved using our telescopes. The geographic impact, you can see that in the last year, there have been 41 countries involved in the Global Sky Partners program, a quite colossal reach. But the reason for showing you this is that many of the programs take place in a language that I don't speak, Portuguese. And we have a very, very strong program happening in Brazil that's delivered in Portuguese, something that I never would be able to do myself. And we have partners that are localized. So they deliver a program to an audience in their own language, not in English, but they deliver it in their own language. So that has obvious benefits to this sort of franchising. The demographics in the last year, we were perfect. We had 13% that were from underrepresented communities, but a larger number said that they had mixed representation in their communities. So these were people who were representing groups that were from, say, inner cities and things like that. And 74% of that audience was high school students. We've had a lot of publications in this last year, 20 in the Journal of Double Star Observations, which Rachel Freed is the editor, and 4 papers in other peer-reviewed journals. Plus over 20 exoplanet transits were submitted to the AAVSO database. And since the program began, it's over 130 papers that are published by high school students, not by undergrads, not by the people who are leading these programs, but by high school students. 18 talks were presented by high school students at professional conferences. That's really quite mind-blowing to me. When I was a high schooler, I would never have had the confidence in my own abilities or what I'd done to give a talk at a professional conference. And these are some of those students. I was very lucky to see 2 of them presenting theirs at at different conferences. We do an audience survey, and 98% of those said that they could contribute to science. These are very, very general questions, but they show the confidence and the scientific identity of people involved in these programs. So these are all the different people who are giving talks on their Global Sky Partners program using Las Cumbres Observatory. And Miracle has already given his talk in Division C, but the rest will be giving their talks over the next few days. You can see all of the partners on our partner showcase on that URL. But really, I want to say thank you, not just for listening, but for all the partners, because without them, this program wouldn't exist and wouldn't be possible. And it's really due to their hard work and their devotion using that this program has been successful, and using robotic telescopes has had such an impact on all of those people. So thank you.
Thank you very much, Edward, for the talk. We give him another round of applause. Yeah, so I will not open this one for questions because we have a long discussion session where questions will be asked to Edward. We've exhausted the 10 minutes. So I'll call on the next speaker, Michelle Jebadi. Michelle has been director for the Office for Young Astronomers, so she's so deeply involved in education. She's also one of the pioneers for the Astrolab project, where we've been using Las Cumbres telescopes. Sure, but you.
Thank you. Thank you very much indeed. Thank you for the introduction. So it's done. What I will say as a rationale is that we know that scarce funding limits very often the capacity to implement lab activities. But we know also that astronomy is an excellent science to teach students about the science method in a very attractive way, and the availability of remote and robotic telescopes open new possibilities at no cost, provided there is a free access, of course, to such telescope. So what we have tried to develop some time ago with Jean-Pierre de Grève and colleagues that you saw on the previous screen is that Astrolab was created in this context expressed before. It is an inquiry research method through threefold objective: introducing students to the scientific research method, enhancing interest in STEM fields, and offering the above and initial support to universities without any cost or expensive astronomical infrastructure involved. So what is doing Astrolab? Pose an astrophysical questions to address a real interactive astrophysics experience. In performing this lab, the students will go all through the various steps taken by a professional astronomer planning an observing run. How is working Astrolab? Astrolab, being an inquiry lab activity, has an implementation very flexible. It can be a compulsory or an elective course at undergraduate level, an elective subject for BSc diploma. It can be also a part of curricula for engineers, for example. But given the learning by doing character of Astrolab, the autonomy of the students, they choose their objects, they plan their observations, they request the observations, they analyze the data, they discuss their observation with peers. The students need significant coaching, monitoring, and assistance from a tutor. So the tutor training is really the key point of the implementation and then of the success for the students of Astrolab. So this is why we have developed a website for tutor training, which will be open and available from the OED web pages in a few weeks, simply because OED is refurbishing as some other website page for the union. So it will be open in a few weeks. It's still there, accessible from the company who is doing the job of implementing it. So we have developed a website for the training of the tutors and slightly more as I will try to explain it to you. It starts with a general page which can be seen by everybody. You see there is no login necessitated. The login is still there on the right side. And you have a presentation of the Astrolab. And all these pages can be read without registration. But the next step going to the training can be accessed only after a registration. So That's why you see the logout here. So how it's going on? The training will provide training for the tutors in the form of a tutorial. And not only there is a tutorial, I will come back to it very soon, there is also a project management, as you can see here, support, which offer to the tutors a guidance through the process of guiding the students all along the weeks or the months of using this activity as by sea, for example, or general course in astronomy, astrophysics. What is going on in the tutorial? The tutorial guides you when you log on as a tutor through all the processes of taking observations and analyzing the data and given the results. It contains a comprehensive set of exercises to obtain. We have selected as an example an eclipsing binary star using the Las Cumbres 40 centimeters telescopes. And we are very thankful to Las Cumbres Observatory for having support our program since it was open to the possibility to apply for it. For each step along the way, the tutor has examples and it invites the user to carry out themselves these examples. And of course, the results of the examples are given. The tutor training includes also a set of presentations that can be used later on during the classes, and of course, the answer of the exercise used during the training. All the images needed from this training already taken at Las Cumbres Observatory are given. But of course, you can use absolutely any telescope. It's totally general. The training is general, except that what is provided for the first step are the images of Las Cumbres Observatory. All these documents are freely available and can be downloaded after registration. Even if the tutorial includes some background information on astronomy, astrophysics, where it is referred to these manuals during the tutorial, which can be downloaded, it is not an astrophysics astronomy course. The minimum of background is reminded here. It is conceived to be part of a general astronomy course or a compulsory or whatever it can be. All these documents are freely accessible. You have the list here. They can be downloaded directly after registration. All of them are in PDF, as well as a PowerPoint, which has been transformed into PDF in order to be sure that everybody can read it. And the tutorial is not aimed to be done online, but at the tutor pace without need of a link to internet. So I will say that to conclude, Astrolab is now a website for tutor training after being something where we have been going to different universities, different countries, Zambia, Zimbabwe, and so on, to develop this website among tutors. But Astrolab guides you through all the process of taking observation, analyzing the data, simply through a set of exercises. Better if you can use robotic and remote telescope, better if you can use a reset to LCO telescopes. I will tell you why. Because you have 10 telescopes around the world. If a student is sending a request to observe, for example, during the next morning for the breakfast, during the breakfast, you can have a look to the images taken, which is very much appreciated. Astrolab contain also example practicals which are given. It includes manual which can be used during the classes, and the presentations are part of it. Project management have been found to be useful not only for Astrolab but for our teaching at the university with undergrad. Thank you very much for your attention.
Thank you very much, Dr. Michelle. I'm just been reminded by the technical team that when we are speaking, let's speak closer to the mouth, to the mic, because we have people online. So if we speak off the mic, then they cannot hear us. Once again, we give a round of applause to Michelle. All 10 minutes are gone, sorry. So again, we'll have questions for Michelle when we have a panel discussion. So we have plenty of that time. Just keep taking note of the questions that you have for the speakers. Our next speaker will talk about leveraging Ghana's 32-meter radio telescope for astronomy training, Dr. Proven Aziri.
Okay, morning. Yeah, so my name is Provin Ajiri Manuel. I'm from the Ghana Radio Astronomy Observatory, and I'll be speaking on leveraging our 32-meter radio telescope for astronomy training. So I will talk about the setup of the telescope and also some science capabilities and what we've been doing with regards to the DARA training and the Astrophi training, and also there are big data and teacher training and outreach. And then I will conclude. Yeah, so this is our telescope in Ghana. It's 32 meters. It used to be a telecom dish that was left redundant over the years when fiber optic technology came. But we found use for it during the SK and AVN setups. And it has gone through extensive engineering to make it a radio telescope. And we have Roach backend that enables us to do single dish and also VLBI. And also we also are able to do some pulsar observations. And we, of course, also have some servers for data storage and also data analysis. So for science, we are able to do some metal maser observations, pulsar observations. In the continuum, we look at some AGN sources and then some other continuum sources that we use for calibration. And also, we're now beginning to delve more deeper into those ones. The telescope was able to do some good VLBI fringe tests back in 2017 with telescopes in Hatro in South Africa, some of the EVM partners, and then one other telescope also in Russia. Apart from doing science, the telescope is a host to the DARA training. And over the years, we have students from Ghana and 6 other African countries come over to the observatory to be trained in practical astronomy training. So 10 students from each EVA Panther countries. These students would normally have got a good first degree in physics, maths, and all the related sciences. And they do about 8 weeks in total for the DARA training. And part of that 8 weeks, they have 2 weeks hands-on in observational training in metal masers, pulsars, and then also data reduction, and some also computing training. So this is some section on hands-on observation where the students are able to select their source and do some background on the source that they're looking at, when the source will be up, and then they have groups, and then they are able to observe that data and then analyze it the following day. And then apart from that, also they are also able to look at some practical stuff. For example, using a DSTV dish to measure the temperature of the sun, and are also doing some RFI measurements on the site to acquaint themselves with these RFI test jigs. And then also we have a smaller handmade telescope that we call the tabletop radio telescope that you can point to the center of the Milky Way and then take H1 observations from there, and then also analyze the data to see what's going on there. It's pretty cool that the students are able to try their hands on this themselves. And part of the training that we do during the DARA is also the computer training, where the students get 2 weeks in Linux training, Python, and then also VLBI training, which is supported by CHPC South Africa. And then with tutors online, and then local tutors in Ghana, and we are able to help these students during this CHPC training. Over the years also, we've also got some grants from the DARA Big Data, where we brought together about 5 students from 5 universities, and also give them hands-on training in Linux and Python and data reduction. But beside astronomy, they also look at some remote sensing applications, and then also trying their hands on HPC service. Yeah, my colleague Albert also have led this training called Astro5, which is putting together some redundant 2.4-meter dishes on our site, and then put electronics to it, and some motors, and incredibly they're able to work and do some nice things. So this set up for astronomy and also satellite data, and this training actually creates a lot of interest in the students wanting to know more about astronomy instrumentation, and also some applications of the same satellite that you use for astronomy also for remote sensing applications. The observatory is also able to do some teacher training workshops. My colleague Naomi and co have been leading that, and bring teachers who do not have knowledge in astronomy, teach them astronomy and some hands-on that they can replicate back in their classrooms when they get back. And then outreach programs also have always been going on at the observatory. So we aim to continue to expand these activities because over the years, we do get lots of numbers of student teachers who are interested in astronomy, and they want to know more, they want to do more with us. And also, we also looking for funds to expand it so that we can also have some labs that can do some small electronics that they can do themselves, and then also the instrumentation aspect of it. We're also looking forward to doing VLBI and single dish observations of many interesting sources. Our dish is it's not that cool, but it's not that the system temperature is about 110 Kelvin, but we can still do some follow-up of certain interesting sources in single dish. So we also aim to have PhDs and masters from other African institutions, and also from your institution also. You can send your students also down to us in Ghana. They spend some time with our telescope and also contribute to the research that we do over there. Yeah, so in conclusion, that's what the 32-meter telescope has been doing, transformed from a redundant telecom dish, but it's been able to transform a lot of students. I would say more than 100 plus students have been trained through the DARA at the observatory site. And beside that, we could talk about 500 other students who have maybe not regular DARA programs, and then also students that visit, about 2,000 to 3,000 of them. So GRAO is also building capacity in data science and machine learning, and we would love your collaboration to keep going and expand it. And then it's also open to collaborations in PhDs and then also masters. We'll also soon be having some DARA postdocs that will be at the observatory to also improve upon the science that we do. Thank you very much.
Thank you very much, Dr. Proven, for the nice talk. All my speakers today are maximizing the time. They're taking all the 10 minutes. I'm yet to say this about the ODE prize winner. We shall see. Our next speaker is Professor James Chibweze. Remember, he's a co-prize winner for education. James.
Hello, good morning, everyone. My name is James. I would like to show you a small effort we're putting together to make sure we bring Africans to use the big projects that are coming up on the African continent. Of course, you know, one of the big projects is the Square Kilometer Array. I'll start by showing you this. This is what we have on the continent at the moment when it comes to radio astronomy research. Well, there are a few more, but these are the big ones. One of them is the Miaka telescope, which I guess some of you may have visited the site, and that's the same site you will have the SK telescope. And the SK dish, one of the SK mid telescope is already standing on site. So if you haven't been there, please make plans to visit. It's a gorgeous place to be at. And that's the telescope that Proven has just talked about, which I spent 2 years commissioning. This is actually the first time that this dish moved after staying redundant for 11 years. So that's a 32-meter telescope, now functional, not optimally yet, but you can do some research with it. There is a hydrogen epoch of free ionization, which is looking at cosmology, essentially. And here we have a telescope we call the C-band or Sky Survey, which is funded jointly by South Africa and a couple of universities in the United States. And this is our baby that has been there for many years, the Hatrao 26-meter telescope. Unfortunately, that baby is slowly dying out. And this is our new toy. We're currently heavily pregnant with this. Hopefully in another 4 years, we will give birth to an African millimeter telescope. For those of you who were in the session yesterday, we talked extensively about how this will impact the continent and our new contribution towards the Event Horizon Telescope to image black holes. That is super significant because if you want to do black hole dynamics, you definitely need 3-4 more stations on the African continent to bridge your UV gaps. But the key question has always been, with all these multi-billion rand or multi-million euro projects, including what we call the AVN, which was supposed to be a skill transfer project. Okay? And for the AVN, the plan is to take each of these dots, which represent redundant telecommunication dish, like the one that Proven has just talked about, convert them to a radio telescope, and then you have a VLBI network that will be equivalent to the VLBA, the Very Long Baseline Array in the United States. VLBA has got a baseline of about 8,600 kilometers, but you will get as close as 7,000 kilometers if we're able to get this. This is a dream, and we keep it as so and keep pushing to have it. That's the SKA. It's coming. Some of you may have seen this image already, which was released while you were all here, which is image made with the Australian side of the SKA instrument. You have lots of transient science to do with it because it can image the entire sky multiple times in a very short period of time. These are all cool and big, significant instruments, but that's the question to be answered. Where are the African users of these emerging radio astronomy facilities on the continent? If we don't answer this question, the entire global astronomy community may get only 60% because you might be losing up to 40% of the manpower or up to 40% of the discoveries that we need to make. But interferometry and radio astronomy, just like any other astronomy, it's not too difficult, but it's not simple. People need to learn how to do it. And you cannot learn with expensive instruments. If you want telescope time on meerkat, you need to fight for it. No one will give you 10 hours of time to observe with meerkats just to teach people. It costs a lot of money per hour. Therefore, we need a way to expand radio astronomy education and do more outreach. Of course, when people talk outreach, everybody always see this idea of carrying optical telescopes, set it up and point to the sky and people look through it. We need to not reverse, continue doing what you're doing, but you need to add one more step to it. Please carry a tiny little bit of feed or carry a small radio antenna, the one on your radio set, connected to SDR, we call it software-defined radio, put it on your computer, show them some radio waves. If you can take a feed, please show them H1, which is a neutral hydrogen emission from the galaxy. Stimulate that interest when you do outreach as well. That is super important. And this is some of the things I'm keen to do. At Northwest University, I designed this Michelson interferometer. If you stretch out the ladder, you get longer baseline. You can get baseline up to 6 meters, and you can use it to measure the diameter of the sun. And happily, Bonaventure, who's there, requested that I make one more for them, and then I made this, and it was shipped to Nigeria, and it's been used in Nigeria. With the data projects, there is a couple of feed horns being designed with L-band receivers with which you can show H1 detection. So this sort of outreach instrument is cool, but please do not stop at outreach. That will not create the astronomers we need. Basic education is good, but if you want African contribution, we need to go one step further. We need to get those people to understand research methodologies and understand how to do it and get it done. If you stop at this, you're still keeping Africa out of contributing to the global science. So here is an idea I developed a couple of years ago, which I called the Radio Astronomy Network. And the idea is to leave out these 10 million, 20 million instruments. The conversions are expensive for big telescopes. But populate the continent with cheap, very small radio telescopes, which you can use for education, you can use for outreach, and you can use for some level of research. In fact, just the same way people in optical do, you can actually make it available for online usage. And I will show you an example. The Northwest University 4-element interferometer, which was a proposal I submitted to the university to buy 4 dishes. Each of them is 3.7 meters in diameter. But L-band feeds 4 of them and C-band feed 4 of them, and you can put it on the instrument. This is quite cheap, and you can put 300 megahertz bandwidth. Each of the dish will cost you around R500,000, which at the time was probably 25,000 pounds. And then you can use the cheap labor you have in the students so that they can also learn. You ship it from wherever you purchase it from, you get them to put it together. There are the data students that Proven talked about. For all the ones within the Southern Africa where I don't have to request for visas for them because they can travel freely, brought them into South Africa and just get them busy. Feed them properly, and you put them in a good hotel, and you get them to get the job done, and they will be super happy. So those are the students. It's once in a lifetime experience of building your own telescope. I can show you how happy they can get. Of course, you need at least one person who has lightweight. She's the most lightweight one who will go into the dish without deforming it and install your feed system. And then just get a simple TLB and lift things and install them. Okay, the movie didn't play. Let's see. Okay, didn't play, but I would have shown you how excited young people can become when they have to move a 3.7-meter dish to the pedestal and happily assist and instruct the driver to install this. And within 2 weeks, we did 4 of that dishes, tested them, and they were all functional. Okay, and this is what the site looks like now. And that is me right there with my crew, excellent students who have done a very good job. And we've got a dish here, another one here, another one there. This is an area view, so it's quite tiny. And that's the control room right there. Each of the dish is spread out to roughly 100 meters from the control room. So you get a maximum baseline close to 200 meters. Remember, that means I have a telescope that has better resolution than the Green Bank telescope, if I can do interferometry, which is super cool. Okay, that's what the video looks like. I'm going to skip this because it's quite long, but you can always speak to me and see how we went about the construction. So what are we doing at the moment? So after completing the installation, the university decided, wow, now you have a good project. We want to upgrade the site. So those buildings you saw were completely renovated. They took out the roof, upgraded it. The roads is horrible. You can drive up easily. But now we have a nicely paved 2-lane. Your tires can run on up to the hill, a proper gate into the facility. So it took a while. So the site was taken away from us, but the upgrade is completed. We're now making effort to get internet, very good internet connectivity on the site, which means you can very soon be able to use a 4-element interferometer for education, but do that remotely. You can also request for remote observations. Hopefully in another year, we will be able to call for open time, which is good. So it means you have an educational facility to teach interferometry, which is a skill people need to use the SKA, which is a skill people need to use it currently already outperforming other instruments, Meerkat, okay? So look forward to this and use it to train your students. We didn't stop there. We decided to go further to, of course, I am Nigerian, so I would like to give back to my society. We decided to strike an agreement with the Center for Basic Space Sciences, myself and Ross Bonds, who was a fellow student in Japan when I did PhD, and Gordon, who was a scientist here in South Africa. And we raised funds from the public and built yet another dish. And then I had to fly into Nigeria to the center, put this together, got it installed, put the feed on, of course, checked all the things and tested it properly. And this now functions in Nigeria. That's the 5th telescope on the continent, well, which can be used for radio astronomy. But in the case of the Nigerian dish, we already, because there is no site construction to be done, we already can use this remotely. And this is one example. At Kwame Nkrumah University, which is in Ghana, where we conducted a workshop, I made all these students you see here by themselves log into this telescope, which is in Nigeria, drive it to a source and demonstrate or learn to use this remotely, which is cool. And you can see them all smoothly. So again, we have yet another instrument. Of course, when we get closer, when I get additional free time, one more thing will be to find a way to plug the signals between these two countries and show VLBI fringe, which I guess the community will be happy to see. So that's what we have now. I saw in the Olympic that people are now giving cameras to take selfies after winning medals. I didn't win any medal, but I took a selfie with the telescope on site. And that's what our site looks like. That's the road off. It's a terrible road, it's a bit off hill, but now it's a properly paved road that you can drive up. And this is where we stand. That's my dream. So if you have funding lying around that you don't know what to use for, and your favorite country is Madagascar, please just buy me one dish. I'll be happy to fly down to install one in Madagascar. I would hope in the next 3 years that I can populate the entire continent with these small dishes. People can start learning proper radio astronomy, not just looking at H1. They can learn to schedule observations. I know that my time is up. I will leave the stage soon. Sarao is making effort to do similar things. So hopefully we can get here sooner than I would want. Thank you.
Yeah, so when James is in Zambia, he's called Chifu Mukuni. So because I'm his subject, he was ignoring my warning. Now, thank you very much, Professor Chibweze, for that nice talk. We can give him a round of applause. Okay, again, he used all the 10 minutes plus. So I hope you noted the questions to ask the speakers today. So I'll request, do we have any volunteers to help us set up there, put 4 chairs in front, and I'll invite all the speakers to be in front there. Please, you may take your seats. Okay, so all the burning questions that we have, this is the moment. Also, we want to encourage the people that are attending online. If you have questions, we have assembled all the speakers from this session. They are sitting in front, and we'll start getting questions from the audience as well as those online. Okay.
Thank you very much. Hi, can everyone hear me? Yeah, okay. Thank you very much for this interesting session. I have a first question for the talk of Edward. So Edward mentioned that in selecting the proposals, science was excluded. How how do you do that? Because of course, a lot of the students' projects concern science. So it should not be science that is led by a PI that is gonna use it by him or herself, by themselves, but it should involve students. Is that how you decide? Yes. Not really, no.
Okay. So I think the comment, hello, I'm not Edward. I'm Michael Fitzgerald. I also work for Las Cumbres Observatory, and Edward had to go give enough talk. So the comment about it doesn't involve science, it's more about people who run the projects are not to use it purely just for scientific purposes. But if you involve students, then you can. So a lot of projects, maybe about half of them, are focused on student research. So doing things like exoplanet transit follow-up is a big one. Double stars, having a look at stars and them moving over decades and stuff like that. Independent research projects run through high schools, supporting them by giving them telescope time. So it's not that science is excluded. In fact, science is encouraged, but it's not a purely scientific proposal. So you can't just go off and do your own research. So that's the general idea.
Okay, we have a question here and there. Yeah, then start.
Thank you so much.
So as you ask a question, just introduce yourself by name.
Oh, okay. So I'm Sopiri. My question goes to James. So in terms of the budget for putting up, let's say, well, one dish, as you did in Nigeria? What's the estimated budget for the total cost of that? Thank you.
Okay, in the case of Nigeria, I think we spent in the total eventually about £40,000 because we needed additional shipping. We got some extra components, and the transportation was longer than in South Africa. In South Africa, we just shipped to Durban and it was easy to move to port. In the case of Nigeria, you ship to Lagos and it's a longer distance to drive all the way to Nsukka where it was installed. But I suspect if you want to do this in Zambia, we'll be looking at the same cost. There is something I didn't mention. For every instrument existing globally, the bigger cost is the running cost. I always mention you spend 4.2 billion rand, for example, building the Meerkat, but the operation costs a year, including the salaries you pay the people, over 5 years will build another Meerkat, assuming you have to exclude it. So if you're thinking about this, I always want to sit down first and say who will pay for the electricity, who will pay for the students, who will transport to go to wherever it is, who will pay for all these minor things that we tend to ignore, which is significant. So we can source money to get the telescope, but there is always need to talk about the running expenses.
Okay, maybe before we give a mic for the next question, let's get some questions from the people online. They can unmute and speak.
Hello, can I start? Can you hear me?
Yes.
Okay, so this is Ulrich Koll with a question for Michael, Edward. And this is information I might have missed in the talk, but I was interested to know how the usage of LCO, the educational usage of LCO, distributes between university level students and high school students in terms of the number of users on the one hand, in terms of the time used on the telescopes.
So undergraduate students. So as Edward said, we tend not to do, research institution, developed world, undergraduate, under Astro 101, second year level courses per se. We do undergrad with community colleges, underserved communities in the developed world, and then anyone in the developing world. The numbers is something that's inside Edward's head, so I can't actually quite quote on how many people are doing undergrad in the Global Sky Partners program. Would you have an idea, Michelle?
I can answer only for the undergraduate students, and a bit of programs to run BSc. It's about 50 hours a year. And how is it distributed? It depends on the request. The years are given for the program Astrolab, for example. And then colleagues are send me email telling, well, I will teach Astrolab this year with my students. I have 20 students, roughly speaking, for one complete nice light curve. It takes 2 hours in case of bad weather and things like this and failure. So the number of students is always very moderate. What is the university? For example, in a Pretoria University, there are 20 students per year, or sometimes 30 if there are 2 sessions. In Peru, in Lima, for example, that's the same name, 15 or 20 students. So the distribution is going that way. And the number of students link to having a direct link, they do their own observation, is much more smaller than in high school, definitely, much more. Because very often it's a compulsory program, or even if it is included in the courses, there are not so many students who are registering in the astrophysics course at the university. So this makes the difference. roughly speaking, 50 or can be 60 hours in some years. That's the number.
Thank you.
Okay, do we still have another question online? Okay, we can take 2 more questions from the online, then we take from the in-person. Next. Okay, so whenever they have a chance to unmute, they can just speak, and then we will pause from the in-person sessions. I think there was a question from there. Then we'll come to you.
First of all, many
And
thanks to the speaker. And I have 2 questions. The first one is for Michel. My question is how can a network of African observatory contribute to Astrolab? And the second question is for James. Yes, in Morocco, we have just beginning the thematic of radio astronomy. And yeah, I see that what a beautiful network of that you have there. So how can we join your dream? Thank you.
The way we are working is the following. We apply for telescope time every year to LCO. And as you saw, the LCO telescopes, the 40 centimeters telescopes, whatever they are always situated in a professional observatory for safety and whatever it is. And there are 40 similar telescopes accessible. But of course, if there is other possibilities, they are welcome. But we should know how to apply. Is there something to be paid? Because before having the possibility to apply for LCO, we were asking, requesting, and paying for eye telescope. And for eye telescope, the cost for taking an image for a star was about €1, something like this, more or less. And the procedure was different, but we had to pay something, it was paid by Jean-Pierre de Grève University because it's Astrolab has been created by Jean-Pierre de Grève and Nicole van der Blik, also, who cannot be here today. And at the very beginning, we obtained a grant from the OED to set up this program by having training, live training. So any observatory is welcome, really. And for this program, it's only photometry, as you see, because the 40 centimeters are photometry. But we simply need to apply, how to apply. So this is why we have this roundtable on the 15th, at the end of the afternoon, to see how it could be possible to create a link, a common partner, and how to apply to each one. So it has been a large inquiry done, and the results will be given and discussed all together at the roundtable on the 15th.
One more question for James.
Can I respond to the question? Okay. Just before responding to that, African telescopes can contribute to Astrolab. In the African Astronomical Society, we are making effort to bring back some telescope like the Rothschild telescope in Namibia to life. He has actually done his first observations since being brought back to life. So the aim is within the next 1 year to make it robotic, so you can remotely observe. And we will open it, don't worry, we won't ask for €1. You can take as much photometry as possible. So for the Behida, for you can make your telescopes open. If you allow us to use the telescope on top of the mountain for Astrolab, absolutely they would use it. But you just need to create an avenue for them to apply, submit application to use the instrument, probably indicate how many hours you can dedicate for such observation each year so that they know how much they can use it. I'll leave the optical things there because I like radio more. For the radio astronomy, you can participate anytime you want. If University of Cagliari is willing to host an optical telescope, you have a radio telescope, you have very good sites. We've already visited multiple universities. Actually, we've been talking about bringing a decommissioned millimeter radio telescope from the US to Morocco. There is a lot of open opportunities for us to get that done. So we can just speak about it, and you should be in as soon as you want it.
Thank you very much, Michel and James. We have one more question online from Tilina Henatigala, which I will read because he cannot read it right now. So that's the question to Edward or Michael. Are there any successful cases or partners that conduct astronomy research as part of the core curriculum, so not as an extracurricular activity?
Yes, I do it quite a bit. And if you went to the OAE and Division C sessions, there's a lot of talk about curriculum. The curriculum changes every 5 to 10 years in whichever country you happen to be in. But there does tend to be all sorts of spots where you can fit in astronomy research. So in Australia, in New South Wales, they have a 9-month project that kids have to do, things for year 11 and 12. Rob would know more about that, called Science Extension, which can be a large scientific project which is in New South Wales, where Sydney is. In the state I'm from, in Melbourne, they have a smaller version of that. Goes for a few months in year 11 and 10, but they have a thing called a year 10 depth study, where a student can study something in depth. I'm not aware of any high school curriculum that actually specifically says you have to do astronomy research, but there does tend to be spots where you can do it. So in Australian curriculum at the moment in year 10, there's about 3 weeks of astronomy, and you could either do it through making a PowerPoint or a paper mache Jupiter, or you can get your students to do something, get some data from the telescope and do something that attaches to that curriculum area. And what we do is, the curriculum statement is, there's stuff out there in the universe, there's stars, galaxies, and there's the Big Bang. And you've got to do it in 3 weeks, but you can get some data from an actual telescope. You've got 32 students to utilize to kind of investigate this data that you've got from the telescope. And so it's not quite research per se, but you can make it a research-like activity in the classroom. At undergrad, you have a much more flexibility because you tend to have more control over what goes into your subject and when. So yes, there are lots of case studies, and there's Stanford Online High School has a whole subject. That's a bit of a unique situation. But yeah, there's quite a number of projects that do fit astronomy research into the curriculum. You just have to think creatively a lot of the time, but where to put it, and also be aware in 5 to 10 years it's going to change anyway. That's the big problem. But yes, there are cases where student research is attached to the core curriculum in countries I'm familiar with. So.
Thank you. We can have a question from there.
Yeah. Hello, Markus Pösse, IAU Office of Astronomy for Education. I have a question for James. You said that you're preparing future applicants for SKA time, and that is the eventual goal. Can you say a little bit more about how the process is envisioned? So is it similar to Chile with the optical telescopes, that there is a contingent of time specifically reserved for either South African or African astronomers, or is it, are you sending them into the open worldwide competition? I would be grateful if you could say a little bit about the way that this is going to be handled in practice.
Okay, I'm assuming that your question is, when the SKA comes online, South Africa will have a chunk of the telescope time that is reserved for them. The answer is yes, but not in the fashion of Chile's policy style. With the case of Chile, every instrument that comes to the country, you have to sign with the government that 10% of the time goes to Chileans. This includes instruments that they contribute nothing to. Yeah, I remember we did that with ALMA. They get 10% of the ALMA time. In the beginning, they couldn't use it all, but we opened it up back to what the Americans call the open sky. With SKA is slightly different. The headquarters of the observatory is in Jodrell Bank in the United States. In United Kingdom. US is always coming to my mouth. And the member countries get to decide how the time is distributed. There is an advantage. There is a muted statement about 14% going to South Africa. And of course, South Africa would not be able to use up all 14%. So there is a chunk of time that will come to the African continent. But beside that, I'm sure that when the open call comes, there is always that balancing effect that people want to see African contributors on the project in the science direction. At the moment, I can count the number of radio astronomers we have in the entire continent. It used to be smaller than this. It has grown, but it's still not, we haven't achieved the critical mass we need to be able to make significant impact. So yes, there will be not reserved time, as in the case of Chile. There will be some time dedicated for Africans, but I don't think we have users for it. We do have some, but not enough.
Okay, we'll have the last two questions, one there, and I think Bonaventure raised the hand first. We are running out of time, so.
Yeah, thank you. My name is Brett. I have a question for LCO. Do you guys have any public resources available or anything like that for institutions that want to make their telescopes remotely accessible for other kind of outreach programs similar to how you guys do it, in terms of making it either remotely accessible or robotic or anything like that?
Yes, there's two different ways, and come and talk to me about it. LCO has a thing called the Observatory Control System and Target Observation Manager thing. So it's a fully open source observatory management system.
We can.
Very pleasant music to my talk. And some other institutions use it. I mean, in South Africa, I'm pretty sure some of the telescopes use it. It's not my area. Fun? Yeah.
So I'm aware of the public telescope control software and how you can make your telescope robotic. But as far as like the actual implementation of that, or like security checks to make it safely accessible or anything like that, I'd be interested in knowing about. And we can also chat later if that's easier. Yeah.
I'm interested as to what do you mean by security check?
Can pass the mic to James, Bonaventure.
Thank you, moderator. My question goes to Provin. Yeah, thanks so much for the presentation on the Ghana telescope and its operations. My question is going to like a three-pronged question to you. One, how do you manage to run that telescope? How much is the government involved? Are you doing for SKA alone? That's one. Two, how many universities are using the telescope apart from the DARA projects? I'm just wondering if in Ghana, one university that's also offering astronomy, how are you reaching out to other universities within the region that could make the use of that telescope? And three, I expected to actually give us an idea about operation time in terms of usage cost. If a student want to come and do his PhD or master's with that telescope, what could be the conditions for the person to utilize that telescope? Thank you.
Okay, thank you. On the universities, currently we have MOU with 2 universities in Ghana that using and are going to use our telescope for their master's and PhD research. Kwame Nkrumah University of Science and Technology, and then University of Cape Coast. Yeah. So we already have working collaboration with, I think, 4 key universities in Ghana on the telescope usage. In terms of government support, yeah, it's always a very long story. Yeah, we do have some support, but not as we wish we get from the government. And so most of our activities are funded through that and that partners, Sarao and University of California, Santa Cruz, and yeah, and some other new collaborations coming up.
Are you working efforts to suppose those supports stop coming?
Yeah.
What's the plan?
Yeah, we are always on the heels of government. We always hope that it will be good in the short term. Yeah. So yeah,
Right. I know we still have questions, but our speakers are still around. So if you have a specific question for a specific speaker, you can just walk up to them and have a chat to exhaust your questions. At this point in time, I would like all of us to just thank our speakers and give them a lot of so is there any volunteer who wants to summarize from your panel? Like 1 minute, strictly calibrated to my clock.
So you want me to give a 1-minute summary? Okay, Las Cumbres Observatory is great. It's a global telescope network around the world, and we would love to see lots of students and teachers and people using it, particularly in the not developed world. That's particularly our mission. So if you have a project that involves that population, come and talk to us and we'll make it happen. And it's also a good community as well. It's not you on your own. The 41 partners meet up every once a month, and it's quite a active community feel, and everyone solves each other's problems. So you're not just joining up with your project, you're joining up into a little community of people who love to change science education with robotic telescopes.
Thank you very much. Let's thank the speakers once more. You may get back to your original seats. Thank you. If we have people who are presenting posters to do, and you are in the room or you are online, we are giving you an opportunity of 1 minute to sell your poster. 1 minute. So that maybe I'll ask Michelle to come and lead this component of the flash talks. Are you happy to do that, Michelle? So you can load the poster.
Is it working? Yeah, thank you. What I will do right now, it's simply call to come on the stage over there. The people, those of you who are giving a poster, the poster will be has been already displayed this morning and will be once more displayed this afternoon. And the name is poster of the 13. You may find on the program on which screen your poster will be displayed. If you have been sending your poster after the 1st of August, we have no way to know where is displayed your poster. I'm sorry. That's the truth. So there are 90 screens, so you move around to look after your poster. And I expect that you did not find another poster which is very much interesting for you and that you are lost there. For the 15th, the 1-minute presentation flash of the posters will be done this afternoon at the first session in the same way. And of course, the poster will be displayed on the 15th morning and afternoon. So I will call the number, the identification number of the posters displayed today. So let me just opening my screen. It's coming. So we do not know if there are people on the Zoom having a poster display. We shall see. One, okay. So we have been requesting a very short, very short 1 minute poster, which will be displayed for you. Okay, so it's coming. Don't my computer closed, but that's normal, it's for security. Okay, posters, let's go. Okay, it's here. So with the number 590, Linda. Number 959, Forson Albert.
Linda, you can come.
Oh. Yes, for Linda. You're over them. Yeah. One. Yes, it should be yours. No, it's not yours. There have been.
So maybe what we can do, if we have, we can't quickly locate the posters, the people can simply talk and market their posters under 1 minute. Linda.
Okay. Hi, everyone. My name is Linda Striva. I am an independent consultant for astronomy and physics education. And one of the things I do in my work is evaluation of astronomy and physics education projects. So the title of my poster is Evaluation of Astronomy Education and Outreach Projects. What, why, and how. And so this can apply to your robotic telescope projects, and a big component to getting there is figuring out how well are our projects working towards our visions? What are we accomplishing, and what changes could make our projects work even better? So if you'd like to learn more about evaluation or are interested in working with me on evaluation in your project, you can come to my poster or you can chat with me. Thank you.
Who's next?
Second, 959, Forson Albert. Here. No. Thank you.
Okay, thank you. My poster is about design and development of a 4-element L-band interferometer at the University of Mauritius. Not that.
No, it's not. You don't give a 1 minute poster.
We converted 2.4 meters parabolic dish into radio telescope, where formerly MRT Mauritius Radio Telescope in Northwest line. And that is what our poster is about. And our aim is to also do H1 observation with that. So all this project was built from the scratch. You can visit the maybe the poster session this afternoon. It will be displayed there as well. That is all it's about the project.
Thank you. The next one is from Dorothy Hill, and maybe it should be online.
That's me.
Dorothy, are you online? 1 minute.
I'm here online.
Yes, we hear you.
Fabulous. My name is Jerry Bernard. I'm coming to you from Brisbane, Australia, where I'm the head of curriculum development for science at Brisbane Girls Grammar School. And I'm also in charge of our school's remote observing facility, the Dorothy Hill Observatory. My poster showcases how we have integrated observational astronomy into the general science curriculum at our all-girls secondary school. And it provides an introduction to the equipment that our girls use to produce their wonderful astrophotography images. All girls in years 7, 8, and 9 participate in this program, and we generate more than 700 unique images each year by finding space at the end of every school term to deliver what we call our observatory modules, which are all written in-house at BGGS. We use these modules to teach our students about nebulas, star clusters, galaxies, planets, asteroids, digital photography principles, and so much more. Thank you.
Next one, 1114, Miriam Genoun.
Miriam, are you in person or online?
No. No, she's another meeting. Okay.
Okay, we skip.
1467, Andrew Yen.
So I'm Andrew Yen, and I'm a school teacher in Melbourne, Victoria. And I took up school teaching when I transformed from being an amateur astronomer, where I was showing people the sky through eyepieces. You go to a field and show a whole lot of young people the sky, and they'd have a great experience. They'd say, "Wow, isn't it fantastic? We've seen the craters of the moon, or we've seen the rings of Saturn," and they'd have this exciting experience, and it would translate to nothing. That was a great experience for them, but that's all it was. I got an opportunity to join a school and work with their new robotic telescope, and that transformed what I was seeing was the impact in young people, because they would get involved in in-depth projects. It maybe wasn't quite so much wow, but they got a lot more involved in the projects. I saw the transformation in the opportunities in these kids, and it actually encouraged me to change my career and become a teacher. So that's what my post is about.
One 1795, Rachel.
Hi, everyone. So my poster is about an astronomy for undergraduate student curriculum using robotic telescopes. So we have an entire semester in the United States, a semester-long curriculum using the Skynet telescope network to learn the astronomy that you learn in Astro 101. And we've been doing educational research on this project and looking at the amazing increases in self-efficacy or confidence around this, the students using the telescopes and learning astronomy. And we're looking at the development of the sense of project ownership and science identity. And that is what my poster is about.
To 548, Abirup Data, on automation of the Dongla Observatory on proposal to include it as a next one, 3015, Maria Lebron, the use of robotic telescope in astronomy and physical science. Thank you.
Hello, good morning. My name is Mayra Lebron, and my poster is about the experience of the University of Puerto Rico of the Sky Partner project. We have at the university level, we use the Las Cumbres telescope to do a research project in the astronomy class, general astronomy, and also a general study class where students are not science in general, at the university level, and they participate of a research project. In particular, we are doing a double star project, and they go through all the research process up to the publication of the result in the double star journal. They have been participating on that project for more than a year in a different semester, and we have our students publish at least 5 papers in the Journal of Double Star, and also some of the students have presented the results in local meetings and also international meetings. That's what my poster about. Thank you.
We went for three. Morgan Christian.
Thank you. My name is Jan Christensen Dalsgaard from Aarhus University, and this is really a work led by Carsten Brogaard at our university. The poster is entitled FUT, a telescope, FUT, it's a Danish acronym. A Danish telescope in Australia being remote controlled by high school students in Denmark. So it's a telescope set up at Mount Kent Observatory in Queensland in Australia, financed by the Novo Foundation and remotely controlled and from Denmark. And the idea is that the students should be able to do their observations during the day in the class time when it's night in Australia. So the telescope has been working for a couple of years now. It's very popular. The teachers sign up for time on the telescope, and then they carry out the observations based using a web-based interface to the telescope. There's a camera, CCD camera, so it's all done taking pictures. But then there are also projects defined as part of this to, for instance, do photometry, color magnitude diagrams, but also just to make nice color pictures, and the students love it. So this is a Danish project so far, but of course it could be extended and the model could be used elsewhere also. Thank you.
Yeah, I think that's our last speaker, Isha. We still have another one?
No.
Okay.
But maybe one question. Does all of you know in which computer your poster will be available? Okay, so I will let you know.
Yeah. Okay, so let's take this moment to thank the speakers for the flash talks. Thank you. We meet again here in the afternoon for another set of presentations. Thank you.
Okay. So, hello everyone. I'm Abdelmajid Benida. I'm a member for the SOC of Focus Meeting, this Focus Meeting. I'm charged of this session, so we can begin with the call of Catherine, yeah, for the proceeding. Yes. So, thank you, Catherine. So I let you.
Hi, good afternoon. I'm Catherine, and I'm also one of the co-chairs of this meeting. And we want to just, some of you might have heard it before because you were here this morning, but we briefly want to announce for those who didn't join this morning that for the proceedings of this meeting, we get 50 pages in the book, which is the proceedings of this conference. No abstracts are allowed, but that means that we cannot give everyone a contribution. And we thought about this. We find that a pity because everyone who presents, we want them to contribute. So we decided to make a text that discusses relevant aspects of what has been or will be discussed here. And to shape this overview document, we want each of the presenters to write a short text of maximum 2 paragraphs, about half a page, 2,000 characters, about what you presented at the meeting. And when you do that, you can touch upon what is the status of your project. Do you have any best practices that you would like to share, challenges that you encountered, and recommendations based upon your experiences for using remote and telescopes for observations, robotic telescopes. We have a Google Drive where we will collect these, which I will share by email to everyone who is registered as a presenter for this meeting. We are also collecting a list of online resources that might exist. For example, for Astrolab, there are online resources. So that will also be collected on that Google Drive. And here you see an example of a text that we have already written about the Astrolab that you can use as an example. So that's all I wanted to say. Thank you.
Thank you, Catherine. So for this session, normally we have five speakers, but I think that we have Dr. Naira Rodriguez. She's in there, she is absent. So we have only 4 speakers, and each one will have 10 minutes. And like this morning, all the questions in the end of the session. So I will begin by invite Dr. Rachel Field to the first speaker. She tell about authentic research and scientific writing experience using the LSO telescope network. Dr. Rachel, thank you.
Hi, everyone. Nice to see you. Welcome after lunch. So I'm going to talk about the astronomy research seminars that I run and the impacts on students. And so I'll just jump right into it. So we use Las Cumbres Observatory Global Telescope Network, and I run a double star astrometry research program. This is what I think sort of the simplest science, the simplest astronomy you can do with publishable results. So we run this either from an 8-week seminar or a semester-long program where students go through and they get learn how to access databases and select double star systems to study. They use the LCO remote telescopes to collect their own data and analyze that data. And then they write up their results for publication. And this is one of the things that really makes this program stand out for me and for all the students. For almost all of our students, they've never written anything scientific before. And so they're learning how to not only do the science and analyze the data, but how to communicate their data. And one thing from this list of authors on this paper, you can see there's students from high school, from colleges, there's instructors. Well, I know there's instructors from colleges. So we have these mixes of teams of students working together. We have an NSF grant program, and this is called the USA Sky Partners, and we are developing all these materials that we then just give to teachers. When teachers run through this program, they then just have access to all these resources. One of the great things is we're translating everything into Spanish so we can reach a much broader audience. So we have video tutorials and reading assignments, and everything's being translated into Spanish. So students publish in the Journal of Double Star Observations. This journal itself exists because the double star measurements go into the Washington Double Star Catalog, but they need to be published first. So this journal's been around for about 20 years to capture all of this data. And you can see over the past several years, I joined this project in about 2016, and we have up to now we're getting 30, and actually this year there'll probably be closer to 40 student publications in this journal. So they're really contributing. They're contributing now to more than 50% of the articles, and so they're really contributing to this little area of science, which is really impactful for students who have never done scientific research before to actually contribute to the science. And when we teach these seminars, we often have experts join in our Zoom meetings, so students get to interact with the larger community of practice, the professional scientists or people, amateur scientists that have been studying double stars for 40 years just for fun. So they really get to be involved in the larger community. Just to show you a little bit of the reach, this is just from one semester. I have students and educators from all of these places within the United States and globally. So we're really trying to make this accessible. I really believe in sort of making this accessible to anyone around the world, whether or not you can, if you have money for this. So we try and get grants. I get supported by foundations and businesses sometimes to allow students and teachers anywhere to take this program and really get this introduction to the scientific process. I will say I need to update Edward's slides from this morning. We had 9 papers published just in the past 10 months. He mentioned 20 articles from LCO students in the Journal of Double Star Observations, but I'm pretty sure it's significantly more than that. So these are students from all over that are learning how to write. And one thing that's really amazing, let me go back and come to that, is Edward talked about, and Michael, I think, talked about you're joining this community of practice, this community when you join LCO. And we have global Sky partners that help other students, other teachers. So I had 2 students who were sort of taking, 2 students in Ukraine who were taking a long time to do their paper, and I wasn't able to get back to them as quickly as they wanted. And so someone from Nigeria jumped in and said, hey, I can help you. I've now done this. And they worked and published a paper together. So it's really an amazing community to be a part of. I do research on students doing research programs and using telescopes. And one of the things that we've found, and this is both for students doing, well, I'll talk about students in an Astronomy 101 introductory astronomy courses, we found that using the telescopes, remote telescopes, closes the gender gap in their self-efficacy. So the women in the classes come in with lower self-efficacy most of the time, but over the course of a semester, their self-efficacy increases, both for men and women, but we're closing that gender gap. And self-efficacy is one of the most important predictors of persistence in STEM. So this is really important. I've interviewed students and written several papers on the students in the research programs, and they can be really transformative programs. Students will come in and do one research project and say, what else can I do? I want to do another one. And then they'll do a second one, and then they'll start teaching the seminar with me or with someone else. And it can really transform lives. And so it's an amazing program. Anyone who's interested in learning more about this, there's a form there that you can just fill in your email address and whatnot. And I'd love to introduce anyone else who's interested and your students to this introductory astronomy research process to help build scientific capacity. And that's it. I think that was under my time, maybe. Thank you.
Thank you very much, Dr. I think the first invited speaker for this session. So we switch to the next speaker, Megan Debate. So sorry for the name. So the title is Observing Experience for Undergraduate Student with the Skynet Robotics Telescope Network. Thank you very much.
Hi, everyone. I'm May. I'm a graduate student in the US, and I'm part of the team that runs the Skynet Robotic Telescope Network. I'm going to give you an overview today of kind of what Skynet is, how it works, the curriculum we've developed, and also just some updates because we're making some fun improvements. And so you all get to see like the first sneak peek of it. So Skynet started in 2004. At the time, it was 4 telescopes at Cerro Tololo Inter-American Observatory, and they were designed to detect optical counterparts for gamma ray burst. But in the past 20 years, it's evolved, it's expanded, and since it's served middle school students, high schools, universities, professional researchers in a wide variety of areas. So we now have telescopes in 5 countries, including Australia, Chile, Canada, and they're mostly around half-meter class telescopes. And we also have one 20-meter radio telescope with 6 more radio telescopes slated for integration to the network next year. A lot of these telescopes are actually owned by our partner institutions, so like campus telescopes, and they're operated still by those universities, but they're on the network to give access to their students and give their students access to other scopes as well. And if you're interested, come talk to me because Skynet is compatible with most commercially available software, existing observatory systems. We put our 50-year-old telescope on the network, and that was a process. So if we can do that, we can do any telescope. So when you're actually using Skynet, what does it look like? You come to the website, and pretty much that's your one-stop shop. So you can submit a new observation, like in that portal. You can manage your observations, see the status of them, maybe call out your students who said they submitted their assignment 2 weeks ago, but you saw it was submitted this morning. You can take a look at the live status of any telescope on the network, see what can observe, what's unable to observe, and see a live feed where you can see the telescopes moving around, which has been a great tool for kind of reinforcing to students that they're actually submitting real observations on real telescopes, and they're not just pulling images from an archive. We've also developed some curricula that's designed to use robotic telescopes. The first one is Opus. It's structured like your standard university science lab. And students use the cosmic distance ladder to learn about parallax, that the Earth is not the center of the solar system, and things like this graph, which is distances using standard candles. The second one is MWU, and this one has been kind of my passion lately. And it's set up a little bit differently. It's like a hybrid lecture with in-class activities, and it's a great way to bring in a STEAM aspect to the course because it focuses on students creating astrophotography, interpreting the results and seeing what the color in their images tells them, and then publishing it in an informal blog post. So you can see some examples of student work here. And it also is an opportunity to engage with students who are maybe less comfortable or have been less supported in mathematics. And it also lets us kind of teach some skills that are overlooked, like communicating effectively in science. Skynet also supports student research. This is my undergrad research. I'm from Michigan, where it snows for 6 months, and I couldn't get enough data with my campus observatory. So I had to learn how to submit a proposal and apply for telescope time, use that time effectively, and analyze the results. And so there's a lot of examples like this, where students can do research. Very recent, but unexpected. Last week, while a bunch of us were here, there was a gamma ray burst alert from the Swift spacecraft, and groups of us from Skynet, from Photon Ranch and LCO, we came together and we were able to collaborate and get enough data that we got confirmation of the optical counterpart to this gamma ray burst. And there's 4 students on this detection notice. And because we were working together, we got enough data that we'll be able to actually analyze results and publish a paper about it later. So this is a great opportunity for students and just collaborating. Like Brian said in his talk yesterday, collaboration is very important in the era of big science. And so this is really exciting to look at collaborating between networks. So this is all work in progress, but this is the first sneak peek at what we call Skynet 2. We're overhauling the entire system, the user interface, the API, the database, telescope control computers, weather monitoring. You'll be able to have better hardware management. The whole, if you can think of it, we're probably fixing it. So these are some sneak peeks of the optical observation editor and the ability to add observing events and block out time on your telescopes for different groups. And this is actually a demo of our radio observation interface, just a little sneak peek. And This is exciting because we're also going to have different levels of interfaces with the idea that people of all experience levels will be able to submit observations. We're even looking at the ability to go down to like primary school, like upper primary school level with kind of beginner interfaces to help. In addition to Skynet 2 and just the general Skynet system, we also have the web app Afterglow Access. It's designed to kind of be a multi-purpose tool to help students. You can do basic data processing, so aligning, stacking fits images. You can do photometry like I have here. This is actually for a gamma ray burst. And you can do color and display adjustments for astrophotography without as much of the learning curve as like Photoshop. And Daryl is going to talk more later this afternoon about Afterglow, but you can ask me, Daryl, Rachel, you can ask any of us about it. Daryl's also going to cover, but I'm kind of stealing the spotlight a little bit. We have these plotting tools that are all also on a web interface, and it's designed to help students analyze data of different types, not just Skynet data, any data they collected. We've analyzed data that we got on other telescopes ourselves, but it's just there to support students and being able to learn no matter where their data is coming from. So you could even potentially get data yourself and give it to the students and let them mess around with analyzing it if you don't want to have the investment of them taking the images as well. So like I said, Rachel, Daryl, and I all work on the curriculum. If you're interested in putting a telescope on the network, you can talk to Daryl and I. And with that, thank you.
Next talk is about science and discovery in the classroom, the GLASSy project with Dr. Rosa Dora. Thank you very much.
Okay, good afternoon, everyone. Now I want you to look at that picture over there. It's Gustavo Rojas. I'm going to be him. So now I have a beard and I'm really tall. So this is a project from my organization that was coordinated by Gustavo. It ended already. And it's a project that there was a special call from the European Union, European Commission, for projects that were supporting teachers to work online with their students. So there was a special call and we applied for this one, hoping to bring astronomy to the students using some ideas that I'm going to present here. The project was approved. And these are the partners. Well, it's not important to waste too much time there. So the idea was to create a series of activities that could be used in virtual classrooms using robotic telescopes and other kind of activities, and to attract the students' interest towards astronomy in an interdisciplinary way. So we were hoping to have teachers working collaboratively, different subject domains, different grade levels, and bringing astronomy to while delivering their curricula. So as in most projects that our organization does, Nucleo, it's my organization, by the way, we want to transform students into researchers. We want to bring robotic telescopes to the hands of students, and we want them to feel and learn like using the scientific method, understand how science works. And we do this for all grade levels. So the project produced a training handbook, a toolbox, some activities that we call demonstrators. We had also an assessment toolkit to help educators assess the students while working in the project. And in the end, there was a roadmap. As you can imagine, 3-year projects are never good enough for us to make it the way we want. So in the end, we always end this with a sense of, I wish I could have done this or that or that. But in any case, it's better like this than not doing it at all. So the main topics that are there in the material is robotic telescope, planetarium software, astronomy and space exploration simulations, analog space missions infrastructures, teaching tools, and data science. All of this in a sneak preview. We didn't intend and we didn't manage to have all teachers diving into it and becoming proficient on that, but at least they started to understand that they can use this as an education tool. They can use this as a powerful learning companion for the students to improve their scientific mind, to spark their creativity. So the scenarios, we created 20 educational scenarios, and this was enough to get us started and get inviting educators to be with us in professional development opportunities. So as if you remember, if you were in my previous talk, we first had to convince them that this was good, the engagement phase. We had to provide professional development, and then the rest of the time was devoted to support them in implementing this in their schools. So there were several, the demonstrators used several different methodologies. It used inclusive universal design for learning models. We tried to make sure that we were mapping the curriculum of all subject domains, because we had teachers from biology, physics, chemistry, mathematics, physical education, ICT, history, geography. Many of those teachers were joining us for training opportunities, and we felt the obligation to give something to all of them. So these are some of the demonstrators that we had. That we produced. They are online. You can go there and see if you like them. Most of these were not new creations. They were just revamp of existing activities that we just improved them a little bit to make sure that they were 100% online proof, so that teachers could deliver to their students in an online fashion, and that students and educators wouldn't feel lost while applying it. Luckily, towards the end of the project, the pandemic was going away, if we can say so, and we managed to gather with teachers face-to-face in face-to-face events in Greece, in Austria, and in Portugal. We had 3 of these events, and these teachers felt empowered enough that they not only implemented the activities with their students, but they also created new ones with us. So we managed to co-create with them activities that for sure are going to be very sustainable, because it was created by them for their students. So this is actually a very good ending of this project. So we had some success stories of children observing supernovas or tracking comets. There are more such stories to tell. I don't have time to leave you there for a long time, but I can tell you that the familiarity of the teachers with the tools like robotic telescopes, SALSA J and image processing software, analyzing archives from LCO, for instance, and retrieving image to do new science, they felt much more comfortable later. Their perception of how astronomy is a valuable topic to deliver their curriculum also greatly improved. And also something that we've been working for many years, since 2004, actually, my first exposition to this kind of programs is to have educators understand that they can and should use robotic telescope. So their confidence also was greatly improved to the use of robotic telescopes. So I'm not going to go into each of them. Gustavo was very confident that I could do this in that 10 minutes. I can't. So, but the presentation will be there for you to take a look. And so we plan to continue using this material, and we are already integrating this in our future projects. We have some testimonials to show to you that teachers found in the supporting activities and the follow-up activities an opportunity to find equal, like-minded people, and they felt very inspired to continue, even if they participated online and not face-to-face. And they were all converted to the fact that using robotic telescopes brought a lot of enthusiasm to their students. It's completely different showing an image in a PowerPoint or telling them, go and take your own picture of this galaxy or that nebula or that planet or something like this. So it brings, for sure, intrinsic science motivation, and that doesn't go away. So students start to treat science in a different way. And professional development for educators increase their confidence in embracing the unknown and the territory where they might be completely oblivious to. I end by stealing 2 minutes of the presentation to talk about a new project that we have that will affect you all. You all will be hearing me knocking at your doors, which is called Astro Journeys. We want to create this repository of resources and online training for these resources. And you might think, oh no, my God, another repository and another training MOOC or something like that. But this one is a little bit different because we want to make a collection of hands-on activities where the students will learn by doing. Only those activities are going to be populating this repository. The backbone will be the big ideas of astronomy, or big ideas in astronomy. And the MOOC that we're creating is called Journeys, which will be how to help educators use that particular resource or example that we are sharing with them, which many of you have already recorded, how I use a robotic telescope, how I use a radio telescope, how do I observe variable stars or whatever, how do I do that? And yesterday, after, if you didn't participate yesterday in Division C meeting, you should have, there was a very important presentation about how to support people in conflict zones. And I think that Astro Journeys have a very good opportunity of being a repository of resources, a support hub for supporting material. And we just miss the human part, which is to have a network that will be there 24 hours a day to support educators or people that are in conflict zones and are willing to have our help. So this idea came to me yesterday. The coordinator of the project, which is Sergi University, doesn't know about that yet. But if Jose that is here doesn't stand up and say, no, you cannot do that, I will continue. He is also guilty for me being here, for me doing what I'm doing now. He was my first inspiration for this. And we really intend this to be something that starts with this project and continues for a long time. So all your help will be very welcome to make sure that Astro Journeys is something that is worth being used by educators across the globe, by students, and by anyone despite where they are and what they are doing in the world. Thank you.
So maybe before I call the last speaker, can we check if, please, Dr. Naira is online?
Yes, I am. Hello. Can you hear me?
Is she online?
Yes, I am.
So if she can share with us the screen.
Yes, I need, if you can hear me, I need, okay. I need you to give me permission for sharing. Can you hear me?
Yeah, can you help us, please? Yeah. So, Dr. Naira Rodriguez.
Yes, can you hear me?
Yeah.
Yes, I need someone from the technical part to give me permission for sharing because you are still sharing the previous presentation of Rosas.
Okay, they are doing.
Thank you so much. So maybe can I start and then I share?
I think now you can share.
Not yet.
Can you? Ah. Can you try again, please? Can you hear me?
Yes, yes. Now I can.
Yeah, yeah. Just try to share your again your screen, please.
Okay, can you see it now?
Not yet, yeah. Okay. Yeah.
Okay, perfect. Thank you so much.
Yeah.
Okay, so
you can go ahead. Thank you very much.
thanks a lot. So hello, I'm Naira Rodriguez, and I work as an Astronomy Education Programs Coordinator at the Institute of Astrophysics of the Canary Islands, the IAC. And today I would like to introduce you to one of the educational projects that we developed that is called PETER. PETER stands for Educational Project with Robotic Telescopes in Spanish, and it's an inquiry-based online lab that allows schools to carry out their own observations and research projects in astronomy using robotic telescopes. And our main target audience is the Spanish educational community from primary to secondary school and also vocational training. But PETER is also open to non-formal schools, science clubs, and associations that carry out astronomy education or outreach activities in Spain, as well as to schools from other countries that collaborate with Spanish schools. We currently have over 470 users, reaching thousands of students each year. So, how we did it, we get there. One of the first steps in the design of any project is to know our target audience, their needs and interests. And this is what I did when I joined the project in 2011 to launch a survey among the schools participating in teachers that were a few dozens at that time, and also to open it up to potential users in Spain. And the survey had two main questions. First, what would you like PETER to offer? And from the possibilities we presented to them based on previous research, the most popular were first, pre-designed scientific projects, followed by open observing proposals, then didactic units, and predefined observations. And the second question was, what barriers would you identify to develop these projects? And the teachers' answers were basically two: a low level of knowledge of astronomy and the specific tools needed to develop astronomical research projects, and that it's hard to include inquiry-based astronomy in formal schooling. So the next step was to set the project objectives, and we defined PETER main goals, which are that students discover science by doing science, that is, by participating in real research experiences, to stimulate interest and vocations in STEM among students while contributing to the diffusion of astronomy, and to train teachers in astronomy and in inquiry-based learning methods. And equally important is a realistic assessment of our resources, both human and material. And our greatest limitation in PETER is related to human resources. For many years, this project had only one person, the coordinator, and currently we are two, a specialist in STEM education, Alejandra Godet, and myself, but both of us are only part-time in the project. But we have a great advantage, that is to have access to observing time on a significant number of telescopes that also have user-friendly portals that it's very important, a very important requirement for educational projects. Our institution, the IAC, it's a Spanish research center in astrophysics that operates the observatories of the Canary Islands. And thanks to their excellent astronomical quality, these observatories host the telescopes of some 60 institutions that contribute a certain percentage of their observing time to Spain. So the IAC made an important commitment to the education of astronomy and decided to allocate part of the observation time with some robotic telescopes to the Spanish educational community, and this is how PETER was born. The first telescope included in the project was the Liverpool telescope, a 2-meter fully autonomous telescope owned and operated by the Liverpool Johns Moore University and installed at the Roque de los Muchachos Observatory in La Palma. And other telescopes that were later incorporated into PETER are the 40-centimeter telescopes of Las Cumbres Observatory, to which we have access by participating in the annual call for Global Sky Partners. And since 2018, we also have access to the 40 and 60-centimeter robotic telescopes of the Open University that we will see later that are installed at the Teide Observatory. All the telescopes I have mentioned so far work with Q-mode observations, which are very, very convenient for schools But some schools also wanted to have a more real astronomical experience, as if they were at the telescope control room making the observations. And to be able to offer that experience, we added to the project the 1-meter class telescopes of the SARA network. And we request second half nights with a telescope at Kitt Peak in the US, and sometimes also with the one in Chile, that allow our students to make live observations during school hours in Spain. And another big robot that is being built at the moment and will be added to the project soon, hopefully, is the new robotic telescope. And if you want to know more about it, I recommend you to look for the poster of Carlos Gutierrez. Okay, so what can be done with all those telescopes in Peter? Based on the results of our initial survey, we came up with 3 different but complementary approaches of active learning. And the easiest option to integrate into teaching practice is to obtain and analyze 1 or 3 color images of objects that can be selected from a list. Our users can select from regions of the moon, solar system planets, nebula, stellar clusters, and galaxies. For this approach, we use the Liverpool telescope and the school's observatory observing portal, which in its simple version selects the right instrument, filter, and exposure time for each object. We also offer an image analysis software especially designed for education. This approach is chosen mainly by primary and secondary school teachers with little or no previous experience in astronomy, and its major weakness is that it does not involve an inquiry-based learning process by itself. Another approach is the use of didactic units, and each unit introduces several astronomical concepts related to the primary and secondary school curricula and provides 1 or more practical activities that make use of archival data. Some of the topics we propose are the structure of the solar system, the force of gravity, or measuring distances in the universe. The type of users who tend to choose this format are also primary and secondary school teachers with no or little previous experience in astronomy. And among the advantages that they highlight about this approach are that it does not require much prior knowledge and that the time investment in preparation is low. And the third option, and the most powerful one that we offer, is that of real research processes, either guided or open inquiry. In the first case, we propose to the teachers the type of objects to investigate and the possible methodology to follow, while in the second is the school group who decide what they want to investigate. The LCO observation portal, the advanced mode of the school's observatory portal, and the remote observations with the SARA telescopes allow our users to perform the open observations needed for these projects. Research projects are usually developed by teachers who attend our training courses, and we also provide scientific and technical advice when required. And the strength of this approach is that the students experience the scientific process in all its phases. And some examples of the research projects that are carried out by our users are the discovery and characterization of variable stars, search, detection, and follow-up observations of supernovae, obtaining color magnitude diagrams of stellar clusters, characterization of exoplanets with transits, asteroids, and comet observations, and so on. And another key point of Peter is to train teachers in astronomy and in the use of robotic telescopes for education. And with this aim, we run several teacher trainings trying to reach different communities. And I would like to highlight the Astronomy Education Adventure in the Canary Islands International School that we have been continuously organizing since 2015, together with Núcleo and other organizations. And to conclude, I would like to share with you a video with some of the moments of this school. I will only share some seconds because I think I'm running out of time. I stop here because I think I'm out of time. And I leave here the link to the Peter website and our contact details. Thanks a lot.
The last one, the last speaker is Dr. Tailania. Sorry for the pronunciation. Hina Tigala. Yeah. So you will speak about sustainable development of astronomy research education in Sri Lanka with remote observation. Go ahead. Thank you.
Thank you. Hi, everyone. If I can get my... Great. Okay. I'm going to tell a really quick, short story. Is the timer running? Or how do I know time is on? Okay, great. I don't see it. I'm going to tell a very short story. Maybe like it's very personal. I haven't really shared it publicly, but maybe like 2 people in this room knows it. So I was about 13 and maybe around 13 or 14 in Sri Lanka. And we had the first internet cafe in Colombo. And we didn't even have like internet at home. So me and my like close friend group, we collected like, we get pocket money from our parents. We collected for 2 weeks. And then we would go to this cafe to use the internet. And we can only use 2 hours because it's very expensive. So first hour we would just fool around, and the second hour we would do whatever we are really interested in, astronomy. So we would read and try to browse for things. And that's when I found out actually this is something you can do professionally as a job. I was like, this is what I want to do. And but we didn't have anybody locally, and we still don't have anyone like professional astronomers living in Sri Lanka or to study. But I found a directory of people around the world, astronomers. There was no privacy back then. So the home address, office address, everything was online, long directory. And turns out that directory was the IAU membership directory, right? It was a one long list. So 14-year-old me started writing to each and every person for 3 months, saying like, I'm a student from Sri Lanka. I really want to study astronomy. How do I do it? Nobody responded for a couple of months. Somebody responded in a few months saying, oh, send me your address. That's it, one line, send me your address. So I sent it, and I went home and told my parents. They were like, who the hell did you send your address to? Who is this person? And then 6 months later, I got a box, and that box had a Astro 101 college textbook, a spectrograph, and a couple of stickers and stuff. We were so excited. I was excited. So we were like 14, 15, and it's a college astronomy book. And we were trying to figure out, okay, we need to study this. So 7 of us sat down every day after school trying to understand what this quite advanced astronomy. So we did that for like a year. Then we tried to teach our other younger students in the school at the astronomy club. That's how we sort of slowly got into it. And those 7 friends back and eventually ended up doing science as a career all over the place, but not in astronomy. But this is the struggle I had in Sri Lanka when I was a student. So for many years now, I live in Japan. I work at the university. I've been wondering, how do I actually how do we develop astronomy in a developing country, but also do it in a very sustainable way. I also want to mention Michael, who tried to get me a scholarship in Australia long time ago, but didn't work out. But a lot of people try to help, and has helped, and that it means a lot. So we just to touch base also. So we had the British, when the British was still colonized Sri Lanka, there was somebody who was doing some observation. That was the first recorded observation in Sri Lanka. And then we had the first astronomy outreach program, and the club, and then the school club. And eventually we got a donation of a telescope from Japan. But since we didn't have expertise, that telescope sit right next to a highway. So you can't do research, because every time a vehicle goes by, the whole thing shakes. So it's for outreach. And so in outreach, Sri Lanka is quite active. The school activities are going really strong. So we are continuing. We have like UN activities, IAU, whatever, but locally, a lot of other activities that are also not related, just doing things. That's actually me around when I was 16, still, yeah. So, but I wanted to find a way that now that I'm in a place that I can do a bit more strategically, how do we do in a way that works and lasting long, that ideally for Sri Lanka, my life goal is that the students who wants to study astronomy should not go through what I had to go through. They should have a better way of doing this. So we created a national agenda for 10 years, because now there are about 10 active astronomers who are Sri Lankan born or from Sri Lanka who are working all over the world. So we created a national agenda for 10-year plan. So to set up the first research program and then the first degree program, and eventually turning one of the physics department into an astronomy department. So today I'm just going to focus on the first part, because that's where the LCO comes into. So we, after so much negotiations with the ministry, we managed to hire first faculty hiring somebody with a PhD in astronomy in Sri Lanka, a Sri Lankan who studied in US. So he was willing to move back to Sri Lanka with his family, and he started the introduction to astronomy course under the physics program. And then I brought in LCO as a partner with these students in the physics program undergraduate. So all the undergraduate students who are interested in astronomy, they start doing very basic astrometric measurements and data analysis, like learning Python. And then we had the first research paper from that group. And then the biggest thing I'm still very proud is that in Sri Lanka, so undergraduate degree is 3 years. And if you're like a 4.0 GPA student, you get to do extra year as a special degree. I think it's similar to some few other countries. So we managed to add LCO as a special degree program in Sri Lanka for students who are actually really good. And so students are very happy. They have a couple of options, and LCO is actually doing observations. LCO is one option. And so we had one student who joined last year and did this 1 year of observation, and so he graduated this summer, and he's the first student in Sri Lanka to graduate in physics with a specialization in astronomy. And he was on TV and everywhere because it's such a big deal for us, one student. And now we have and this university is from the south of Sri Lanka. And then now we have another university joined in, which is from the north of Sri Lanka. And if you know a little about Sri Lanka, we had the civil war for 30 years. And that's sort of like the north and the south and and so in a way, culturally, this is also very important for us to bridge these two universities together. And these students actually speaks different languages. So we all use English, but their native languages are also different. So now this new university also joined. And so we sort of, in the second phase of this project, we have about 30 students join in, which is much more than I imagined. But in the beginning, we had only 6 students. Now we have 30 students, and all of them are doing, as their first project, is a group project focused on double stars, because we kind of want to, get students to work on how to learn Python, how to learn data analysis, and writing a paper, and everything that a research astronomer would require to excel. But I'm not the one who's doing it. Like, people here from LCO network, I get them to do work for me because it's such a rich network. Instead of actually me trying to do a lot of things, I invite people to come and do online workshops. And this is also interesting for students because it's an opportunity for them to network and meet people and so on. And I'm so sorry, Edward, because our project is delayed and so slow. The reason is there's so many protests in Sri Lanka in university. So we have a protest from university students asking for things and demanding things because they do deserve everything they're asking. And then we have faculty protest. And so usually an undergraduate student takes about 6 years sometimes to finish their degree. And then we have community protest. So the university has to be closed. And then there's power cuts, no access to internet, the speed is slow. And then also my time is sometimes limited, so I'm not available. So usually a project that should be 1 year, we take about 2 years. And but LCU has been very patient with us, so thanks. And lastly, I want to wrap up with some key outcomes. So the reason I took a long time and wanted to do it in a proper way was that we are really rich in outreach and we do a lot. But when it comes to research and education, we are lagging behind. But I wanted to find a way that we make a 10-year plan and sort of stick to that plan and bring other partners in a way that fits what we want to do locally. Instead of actually joining a lot of other global efforts, we sort of build something locally and then bring others in a way that fits us. And then because of this effort, we managed to also send our students to like LEAP summer program in Leiden, which is one of the top summer schools in the world. And then in the at the Warwick University, there was another summer school. Because of the student went to that summer school, he ended up getting a PhD position in UK, who's there right now. And also, first paper was published in Sri Lanka with all Sri Lankan authors that are based in Sri Lanka. And also the first person to graduate in Sri Lanka. And then that student's also currently at CERN doing a summer school. So, okay, number of students are really small, but we are still very proud of it because this is how we slowly move forward. So eventually I can let go of this project and it'll run its own, and then there'll be more students graduating. And the reason I actually wanted to share this is that there are so many countries similar to Sri Lanka where you don't have observatories and resources locally, because astronomy is as beautiful and inspiring as it is, it's very expensive. And even if you get a donation of like Japan donated a big telescope, 45 centimeter telescope, but maintenance cost is really high. So sometimes it's a bit unrealistically for a country that struggles with so many other things to spend a large budget in astronomy. But thanks to programs like that are open globally, like LCO, and also very patient like LCO, that the countries like Sri Lanka actually has a bit of hope to develop astronomy a bit more strategically without having to spend so much money on it. And to have to for a university to also agree to include this in their curriculum is such a big deal for us. So I think this is a good model for other countries, even in our region and anywhere else, to like without we spending money developing like telescopes locally, we can actually have access these robotic telescopes around the world, which is much more available, and also expertise that people who have done this. So thank you so much. I don't know if I have more time or maybe I ran out. Thank you.
Thank you very much, Dr. Gila. So, on behalf of you, let me thank to all the speakers and invited them to join the panel. So I invited Dr. Rachel and Megan Dubai from United States, Dr. Rosa Doran from Portugal, Dr. Naira from Spain, and Dr. Tailina from Sri Lanka. So please take a seat for panel. And we have about 25 minutes for all your questions. So, and I have a mic.
So while we're waiting for an extra mic, we are starting for the people online, we are starting the Q&A session. If you have any questions, you can unmute yourself and already ask a question while we're waiting for a mic for the room here. Or if it's difficult to speak, you can write it in the chat.
Thank you, Catherine. So, yeah.
A little more of a comment. I really appreciate seeing how like the use of robotic telescopes has really, I guess there's a lower barrier of entry than there used to be. Like when I did it as a grad student. And I'm just wondering what, for all of you, how are you guys actively trying to get, I guess this is more for three of you than in the Sri Lanka case, but how are you guys actively trying to do outreach to teachers so that they know these resources are available? Because I think there are so many more teachers that would use this if they knew that this was available. Have you guys made some inroads with like science teacher organizations? It sounded like you did in Spain. But yeah, where are you guys at with that? And is that something you're looking to expand?
Just a moment, if you can, you introduce for the participation for question, if you can introduce yourself. So, yeah, thank you.
I'm Christine. I'm the NIAC chair of the United States.
Thank you. So the question is someone from the panel to respond. Yeah. Go ahead. Thank you.
Or
so you can.
So yes. So for me, I go to astronomy or science teacher conferences all over the United States and do workshops on this, where I'll have people come in and get an introduction to it. And then I put on workshops at different in conjunction with other organizations that have programs around the country. So yeah, that's what I do.
Okay. That's a very relevant question, and it's the one that is worth $1 million, I think. It's not easy to get the teachers, even if it depends where you are in the world, of course. The reality is different in different places. But it's not only that those that know what a robotic telescope is will fear that they don't know how to use it, but most of the teachers are oblivious to the idea that they can use it with their students. And you even find people like you tell, oh, I have this 2-meter mirror telescope that you can use with your students. And they go like, oh, we have a telescope at school. So it's lack of awareness at a global level on the importance of astronomy per se, let alone the use of robotic telescope for students. So it's completely outside of the radar of, I would say, 99.9% of the teachers in the world. So going to conferences is a very good thing, but often you are preaching to the converted ones and reaching out to the teachers that really have, those teachers that you really want to reach. It's a difficult thing. Maybe we have to start doing campaigns in supermarkets, I don't know, where we go, wherever we can get them, we go and say, this is super cool, please join us. No, but it's not that they are interested and they just are fear. Is the small minority. Most of them have no idea that they can use it and why should they use it and what is good for.
I think I think part of it too, and you know better than I do, in the US, teachers are not given nearly enough personal development time and enough resources to be able to attend conferences, especially when they're very expensive. But we do have programs. We are doing workshops at conferences, and we also have a program where if you implement our curriculum, there's a teacher stipend that comes with it. So you get the telescope time, plus you personally get a stipend, and your first semester of implementing it, we have 1 hour each week meetings that kind of walk you through how to teach the curriculum to your students. But it seems like, at least in the US, a big barrier is the cost and time that it takes to come to a conference.
we have Michelle, if you can, we have two questions online.
Yes.
And after you, thank you.
Yeah, so we'll start with Nara's question. Thank you. You can
Okay, thank you.
unmute.
Yes, it's not a question, it's an answer to the previous question.
Yes, of course.
Thank you. So it's about how we do it in Spain, in the Peter project. And what we do is go and talk to the education ministries locally and also at the state level. And for that, we have the contact with the teams involved in STEM education. So we propose them the trainings that we can offer to the teachers and the possibilities that we can do after the training with the robotic telescopes and with the Peter project. And we had very good answers from those ministries, education ministries. And we are running in Spain several teacher trainings all along the school year, especially focused on teachers in the Canary Islands, teachers in different parts of mainland Spain, and so on. So I think it's also important to go to the education ministries because they have a powerful network of announcing the projects and the trainings.
Thank you, Naira, for this comment. Yes, there's one more question online from Ulrich.
Yeah, hello. So I'm Ulrich from the Open University, and this is a new question, as it were, and about Skynet, because you advertised integrating existing telescopes into Skynet, and I was just interested if you would be able to summarize the expectations you have from institutions or people who run or have telescopes or even robotic telescopes, if they wish to be part of, would like to be part of Skynet, and conversely, what you offer in return. So what is the deal on offer here? Just a quick summary. Obviously, this probably is too long-winded for everyone, but it would be useful to know the basics.
Yeah, so typically there's an exchange of 10% of the time the telescope is on Skynet, and it goes to what we call the Project Intro-Astro collaboration, and it's for student education use. And so then in return, you also get access to these telescopes, these other telescopes on the network as well, including our prompt sites, which are ones that we maintain in Chile, in Canada, in Australia, but you get access to some of the larger collaboration of telescopes. And as far as like keeping up with actually converting your observatory, we help you. We have software. We can work with you to install it, make sure everything is working. In some cases, one of our engineers has even gone to the site and upgraded things like the observatory dome, things like that. And then basically you're doing the maintenance. So say the camera needs to be taken off and adjusted, or it needs a new filter, something like that. That is on the university who owns the telescope. But you also have the freedom to, take the telescope offline for a bit. We have one university that they teach their students to go to the observatory and sit there and take the images themselves, old school. And so they'll take the telescope offline for a bit, and that's totally fine. And then they bring it back, and their students get access to the array of telescopes still, even while they have it offline. It's more of just being able to share. We take 10% of your time, but it ends up going back to students anyways.
So is there any money exchanging hands, or is it services for services and access for access?
Okay, so now we switch to the room. Michelle, go ahead.
Yeah, it was a question. Is there...
Sorry, can you repeat the last part of that question?
Yeah, I'm sorry. I just wanted to establish if there is any money or payments exchanging hands between Skynet and the institution, or is it services only and help with or access to observing time rather than actual funds, dollars, pounds, euros, or rands?
Yeah, the situation usually varies, but we are a small operation, so we typically work something out, and a lot of times it's an exchange of time. for access. And so it's not usually funds. There are other telescopes that are maybe not part of the existing curriculum, and that's where like having additional credits. But then there is a system that is worked out with my boss, because I am a graduate student, and so he makes the final decisions on those.
Thank you.
Thank you. It's mainly It's mainly a question to Rosa Doran. You show us that many participants to the schools felt confident to introduce it. So do you know if it's possible to introduce it inside the normal curricula in any countries, because the curricula are very diverse, or it will be done by some club or activities outside the school? Have you some answer to this point?
Thank you for this question. This is it's a $1 million one again. This is different across the world. Usually, the teachers come with their astronomy club or science club, and that's why and how they participate. But in countries like Portugal, for instance, we have at the moment a space in the school curricula where they are invited to work in an interdisciplinary way with their colleagues on projects. And this is the space that we are occupying right now. The dream is that at some point the curriculum is going to be more flexible, which is happening already in many countries. Not all of them, unfortunately, that will allow us to implement that. But there are also several teachers that are open to the idea that if they work in an interdisciplinary way with their colleagues, they will actually save time. And we have this experience, but this is yet another obstacle, because not only you have to convince them that using robotic telescope is good, you also have to convince them that working in an interdisciplinary way is good for everyone, for the educators, for the students, for everything. It contextualizes the learning in a completely different way. And teachers are usually not used to that. So the way that schools are operating in most of the world is the 15th century way, not how we should be doing today. So we are doing an effort here in several levels, not only bringing the possibility of doing real research, but we are doing this in a package that brings that the package is not enveloped as we are bringing robotic telescopes to your school. We are bringing innovation and inclusion. And guess what? You get to use a robotic telescope as well. So doing interdisciplinary learning is the new way of doing things, interdisciplinary and inclusive. And that's how astronomy will land in the hands of students through this teacher. But it's a road. We are just starting to walk. We're pioneering on that.
The main problem in many countries is the availability of the teachers.
Precisely.
Overload with stuff.
Exactly.
They would like to do it. Can you introduce it in other countries, mainly Erasmus Plus, that is Europe, more or less?
Well, the Nucleo is known for being the partner that brings any project where we participate to people all over the world. We've been doing this for over 20 years. Any European project in which we participate, we invite people from other countries, and they are coming to join hands with us. And every activity that we do online is now hybrid. That's why in every project that we have participants from all over the world. And that's a success story, I would say.
Thank you. I think that Dr.
Lyra has
add some comment. Go ahead. Thank you.
Thank you so much. Yes, it's just to add a small point to what Rosa said, that, for example, in Spain, since a couple of years ago, we also have in the school curricula, so it's immersed into project-based learning, inquiry-based learning. But so the teachers should be doing this from primary to secondary education. What's the problem? That the curriculum is also so huge that they sometimes find, or many times find difficulties to introduce the research projects into into the formal schooling, but it's in the curriculum. So we should be doing this since two years ago, and also before. It was also in the previous curriculum for Spain. But they need time, and this is one of the problems. If we do, as we wanted to do in astrojourneys, for example, if we give them all the activities, inquiry-based activities, inquiry-based projects, with the link to the curriculum in the different countries, we are doing a lot for them. And for sure, we are going to have more teachers involved because they don't have to spend a lot of time on adapting the activities to the curriculum.
Just to finalize and add to what Naira said, thank you, Naira, for that. In the Astro Journeys, we want to create an AI system that will help educators find resources that are related to their curricula, and also help them in something that nobody said here, but it's also a big problem for the teacher, which is how will I assess my students if they are working in this inquiry-based robotic telescopes, project-based, and then I have to give them a grade. So we are also developing a toolkit on how to assess students based on another project, very successful one that we had called Assess. If you search for assess.nucleo.org, you will find the framework for that. So this is all in the same package.
Okay, thank you. I think we have Edouard and Bonaventure after. Thank you.
Thank you. This is Edward Gomez at Las Cumbres Observatory. So, in your opinions and in the opinion of your audiences, are robotic telescopes the unique selling points that sets your program apart from other programs, or are they just a means to an end to providing high quality data? And actually what you do with the data is the interesting thing.
So for my programs, the students and the educators that are in the programs too, it adds a lot of value using the robotic telescopes. There's a lot to be said for project ownership, getting your own data. I've seen time and again the students, they've taken an image of a double star, and that becomes their star. There's a lot to that project ownership and that building up of science identity. So I think it's much more than just collecting the data.
Okay. Some comment from panel?
Go ahead. So all the students I work with are actually born 2000, after 2000. So they are really young, right? And which is interesting because they don't really see astronomy observation as somebody going to a remote location. They're in the generation that everything is connected. So for them to understand remote observation is quite normal. This is normal. Everything is connected. This is connected. So which for me also, which is such a paradigm shift to understand. I mean, I'm not that old, but I grew up in you have to go to a remote observatory to do observation, and the remote observation became more popular in recent times. So at least for my audience, for them, I mean, I think it would be harder for me to send somebody to a remote location to observe than doing it online, remotely.
Other comment?
I agree. And really, I've seen there's kind of a shift in students because I mentioned in my talk, but we've had students sure that they were just getting images from an archive that these telescopes have previously taken. But with effort, like when I was teaching a course and I had to go on a telescope trip to one of our observatories, I would zoom into class from the observatory and show them us moving the telescope around to help reinforce that they are actually taking this data. And once that kind of clicks, it's very exciting. And it's also a way for them to appreciate the amount of work that goes into observing and science and the scientific process without having to spend all night up and by hand logging observations and things like that. So it's a way to kind of impact a large group, but I have heard a lot that it's the most exciting part was actually getting to get an image back from a telescope.
Okay. You have some questions online?
There's no more questions online. I think we can take a quick one in the room, and then we'll move on to the posters.
Sorry, Miriam. I think that Dr. Nar have a comment to add. Go ahead if you have a comment. Sorry.
Yes, I was just.
Yes, thank you.
It's okay. Thank you. Yes, I was just going to add, because I agree with all my colleagues have said, but just another point, important point, is to have the feeling that they are really contributing to science. And that feeling, it's very, very important. And it's it's how we can engage them into STEM careers, into continue with the scientific thinking afterwards. So I think this is also another very important point.
I think the last question before another.
Thank you, Belinda. Sorry, any of you could just address this problem. I know one of the challenges with robotic telescope is time differences from different time zones. I don't know if any of you has encountered having students or teachers from probably 7-8 hours different from where you are. How did you handle that? Because I realize that is a very big challenge to remote observation. I don't know if you get what I mean. I mean, remote observation, like for example, you're from USA, somebody is in Africa here, the time difference. But how do you relate with such things, address such challenges of time difference in remote observations?
So these are all queue-based. So they've just put in their observations and the observations come back. They're not doing it live. The observations just come back a couple of days later.
Well, as a question, when we are doing the one we did with Stone Age Observatory, you know, how to train the students first how to do the observation. They have an idea how observations are done. They have some, at least a week or two workshop trainings on how to do this observation. So they have idea why the observations are being done. But I realized that while we are doing those workshops, the time there and the time here becomes a very big issue. So I'm just wondering if you have encountered such things and how you handle it.
So one thing we do have is we have a lot of videos that explain and actually are my advisor walking through the steps. So like in our first curricula, Opus, which is more like a standard lab, we actually have guides. He has a series of videos that are just on YouTube, and it will walk you through in sections. And the first part after the background is always the like how to submit an observation. And so it walks you through the form, and there's one for every single lab. So you get kind of a way to step-by-step walk through the form with somebody until you have the confidence to do it with it.
Thank you. I think, sorry.
Yeah.
Just also a very quick comment that, for example, for that, it's very important, the global networks of telescope. As I said on my presentation, for example, we have the Spanish schools have the opportunity to do live observations with the telescope that is in Kirtik and also the one in Cerro Tololo in Chile. And we request the second half night on those telescopes that coincides with the school hours in Spain. So if you want them to have a real experience on how to open the dome and control the telescope and so on, global networks of telescopes that have telescopes in other parts of the world are very important.
Thank you.
So I think the last question.
Yes, and then we'll have to move on just to end in time.
Thanks for the nice presentation about robotic telescope. I'm Bunraksa from Thailand. I believe that there are many people from university and school want to use the robotic telescope. I wonder, do you have any criteria about the selection of the research project or the priority in using the robotic telescope when there are many users want to use the robotic telescope? Yep.
So I can just address that from my project. The criteria only because I can only provide it in English, speaking English and having internet access, but we can take many people. My project doing this simple double star astrometry doesn't use a lot of telescope time. And so we can take many, many people. I've had up to 60 people in a seminar. To me, that seems like many. And there are really no criteria.
From kind of the flipped perspective from like running and being part of the network, we do have, which this is a thing we don't tell the students because it would kind of hurt that whole data ownership thing, but we do have some data linking. So if you have a class of 100 students and they all need to take the same image of Jupiter, they won't realize it, but they did all take the exact same image. The telescope takes the image once, and because it was the exact same image, it distributes it to everybody, just as a way of offsetting the demand on telescope time. But other than that, like Rachel said, we have a queue-based system. So your observation may not come in tonight, but it will come in tomorrow night. And we always encourage students, more or less successfully, to submit their observations maybe a week ahead of time, because surely within a few days, your observations will come back. So.
Okay, another comment from online.
Okay, thank you.
I think again, on behalf of you, we can thank all the panel, all the speakers. So give them applause. Thank you very much. So now we switch to the poster session, and we will call. I think we have 10.
Yes. Maybe who is here online or in person to present a poster? Maybe you can raise your hand. Yeah.
Yeah.
Okay.
So we can one by one.
There's not that many, so not everyone that we will name is going to actually present.
So we have
So
Mohamed Amrar, Priya Shah.
Yes, Priya.
Elisabetta Nari, Aroquimar Bissam.
You can already come because it's just
Yeah.
1 minute, so maybe we
Colin Songras. Thank you. Jor Japeli, sorry for the pronunciation. Jack Noel Star. Miriam Gnoul.
Yeah.
Okay. Richard Gelderman. And the last, Carlos Naira Guterres.
Yeah. Carlos,
How
you are
much
online.
we have?
So we have 4 in the room. And Carlos, will you be able to present online?
Yes, I think so. Can you hear me?
Okay. Yes. Okay, then maybe you can start. You have 1 minute and you can describe what we can see in your poster. Thank you.
Excuse me, just here, I also have an online poster presentation by Yuri Appel.
Okay. Okay, thank you. Then we'll start with Carlos and then you, and then we'll do the room.
Okay.
Thank you. Yeah. So,
Okay.
Carlos, can you start?
Yeah. Can you see me? Okay.
Can we please bring the speaker on the screen?
Yes. So can you see the poster on the screen?
Yeah, I'm asking the people from the AV to bring. Yeah. Yes. Thank you.
Okay.
So we have 1 minute, please. Go ahead.
Okay. So we will start right now. My name is Carlos Gutierrez. I'm an astronomer at the Instituto de Astrofísica de Canarias. And I present this contribution on behalf of the groups at IAC and the Liverpool University in charge of outreach and educational projects. This extends a bit what the presentation that has been given in this session by Naira Rodriguez. Well, the IAC runs the Canary observatories in the island of Tenerife and La Palma, where there are a huge number of astronomical facilities. And in particular, there are a suite of robotic telescopes that are well suited for educational projects. Now, I want to mention among them the Liverpool telescope, which is currently one of the largest robotic telescopes in the world. And well, there are 2 major educational projects called Peter and TSO, one at the IAC and the other one at the Liverpool University, that use a fraction of observing time with such telescopes and allow to participate the students and teachers of secondary school in research projects. So for the future, we plan to incorporate into these efforts also the telescope NRT, New Robotic Telescope, which is an ongoing project to build the largest robotic telescope in the world, and that it is planned to enter into operation in 2027. So that's it. Thank you.
Okay, thank you. Next one. Yeah. Okay. Catherine, where's one? Okay. I think Carlos, no? No.
Is it me?
We
the
have,
next thing?
Yes, yeah, we can see you. Thank you.
Please, can you introduce yourself? And you have 1 minute to present. Can you hear me?
Are you talking to me?
Yes, yes, exactly. You can present your poster in 1 minute.
Okay, thank you. So I'm Andrea Gomboc from Slovenia, and I'm presenting this also on behalf of my colleague Jure Japel. So Go Chile is a project of the University of Nova Gorica and astronomical magazine Spica in Slovenia. It is composed of 2 small remotely controlled telescopes at El Sos Observatory El Saus Observatory in Chile, where observing conditions are much better than in Slovenia. So it is used by high school students, undergraduate university students, also some primary school students and amateur astronomers. It is remotely controlled. We teach them how to plan astronomical observations, how to execute them, analyze data, do data reduction and analysis. And their project basically range from astrophotography to research, mini research projects, particularly, for example, variable objects. Those that are interested, we also guide them to write up their results for publication in some astronomical journals. We also organize summer schools for students and some workshops for teachers. And also we had one science art project related with constellations named after birds in the southern hemisphere. So in 3 years, we had some good results, I think. And that's it for now. If you have any questions or proposals for collaborations, please contact us on this email. Thank you.
Okay, thank you. So just we have to wait how much minute to that this yeah. So the chair yeah. To share yeah. 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 So what is this one? Yeah. This one. Next one.
Okay, so yeah, briefly, we have a project developing a observatory in Kenya. We have at the moment a small 40 centimeter telescope, which is just manually operated there, which we're using for training students in person. But the ambition is to use this, is to develop a proper observatory there with remote and robotic control. So I'm based at the University of Edinburgh. One of the interests we have from Europe is being able to do observations for students in the evening in our time. And Kenya is very good for this because it's a couple of hours east. So in the early evening after classes are finished, students can do 4 hours observing and still finish in a good amount of time. Kenya is also very well placed because it's on the equator, so you can do north and south skies. And so, yeah, this is from a teaching point of view, this is our motivation for looking there. There are some very good mountain sites there to develop a real observatory that we're currently testing out, doing site testing. And yeah, we've done some observations there. We will do more. Then the idea is eventually to have a kind of a meter scale telescope there. And if people are interested in this, come and talk to me or some of the others that are involved in the DARA project. We're around this week. Thanks.
Thank you. Another one, please. Yeah. Okay. No. All right. Yeah. The next one. This one is already yes. Okay. Huh? That's me. You're left, yeah.
Over.
You want to which side?
You want to go?
Yeah.
8 minutes.
Yeah, hello everyone. So I'm Priya, and I teach physics and astronomy at the university, and hence we've been using the LCO basically as an educational tool. We work as Srishti Astronomy, and we are Global Sky partners with LC. So this basically describes one of the projects which we've been doing since a long time, plotting HR diagrams of star clusters using the LCO. And it's very useful because we can actually download even the raw data, make students do CCD processing, use the APT tool or AstroPy for photometry, and then plot the HR diagram. We also give students the option to directly use the Banzai pipeline, the catalog, and then with the catalog also, they can plot the HR diagram. So we do it at both levels for students, and it works out very well. We've done it in online, offline, at different ways. And you can also have a look at our YouTube channel. It's called Priya Hassan. And there are online workshops where we've actually explained all the details in these workshops. Thanks.
Next one. Okay.
Hello, I come from the University of Zululand, which is situated about 150 kilometers north of Durban in the province of KwaZulu-Natal. Now, since this is situated in a largely rural area, learners, educators, students, etc., have very little or no exposure to astronomy and telescopes, apart from a science center, which we have, but that's a little distance away. So we've managed to get hold of a 0.5 meter telescope with the CCD, and this is a golden opportunity for us to train students in sort of all facets, research, education, public engagement, and community development. So we've got the telescope. We've also managed to get hold of the dome, but we are just waiting for finalization of the site where it will be installed, which is going to be roughly about 45 minutes away from the university. And we're hoping that, this will act as an inspiration to learners, students, create astrotourism in the area, and so forth. Thank you.
Thank you. The last one, Miriam Ganul.
Hello. Where's my poster? Oh, yeah, this one, yeah. So, hello, everyone. My name is Miriam, and I am a researcher at Open Observatory of Morocco. And I am the leader of the Pan-African Asteroid Search Campaign. So basically, this is one of 5, I think, campaigns inside a collaboration between the IASC, International Astronomical Search Collaboration, and NASA. And the goal is to introduce planetary science and asteroid science to high school students and university students, but also mainly include them in asteroid discoveries. All right. So what I do basically is that I organize educational sessions for them to introduce the planetary science, why it's important to discover asteroids. Then I organize hands-on session to know how to and train how to use the Astrometrica software to discover moving objects and new asteroids. And I've worked three groups, one in Marrakesh in person, high school students, and two more remotely all across Morocco, including high school and university students. And they ended up discovering few, we call them preliminary asteroid, and they were, Dr. Naira talked about the feeling of contributing to science, so they were so happy about that. So yeah, my poster is talking about all of this, so check it out if you are interested. And for more information, don't hesitate to contact me. Thank you.
Thank you, Miriam. And you have another? Another one? Yeah. So, we forgot someone? Online? Maybe online? No? Yeah. Okay. So Catherine? Okay. So yeah, we want to apologize another time the speakers and for the posters. Thank you very much all. And the end of the session. Thank you all. You have an announcement? Yeah, now for the next session. Thank you very much.
Good afternoon to all of you who managed to obtain a coffee or a tea in a so short time. Thank you for being here. So the last session of this afternoon is mainly, well, I should say nearly totally devoted to observations. And the first speaker is Robert. Please.
Yeah, Robert, just wait before you come up here. I'm the chairman of the session, so I got to talk first. Yeah. Please, I'm strict to time. We've got to make it very smart and very fast because it's the last session. Let us have in mind that the session title is Teaching Capacity of Remote Observing Facilities for the Universities and High Schools. Let that be at our back of our mind, that teaching capacity of those for those who are observatories. Okay, Robert can come up.
Thank you very much. So my name's Rob Hollow, day jobs education manager for the Space and Astronomy Unit in CSIRO in Australia, which is our national science agency. And my side gig is I'm the NIAC chair for Australia. So I'm going to talk to you about radio and remote opportunities and programs. And actually, it was fantastic this morning to see the work that's going on here. I was aware of the Ghana telescope, but it's great to see that new 4-element interferometer and the other small dishes that were deployed in Nigeria and future plans. So it's really encouraging. I'm going to talk about one of our facilities today, and that's Mariang, our Parkes radio telescope, and it's on Wiradjuri land. So I'd like to pay my respects to their elders past and present. So briefly, just going to introduce a little bit about who we are, and then really sort of set the scene before I get into the actual programs and sort of contextualize how we can teach radio astronomy, introduce students to radio astronomy, and then talk about some programs. So we're the Space and Astronomy Unit within CSIRO. We manage the Australia Telescope National Facility, which is radio telescopes and technologies. We manage the Canberra Deep Space Communication Complex for NASA. We also manage the European Space Agency's Deep Space Antenna, and we have the CSIRO Centre for Earth Observation. So our telescope facilities are scattered across Australia. I'm going to be talking about Mariang, the Parkes Radio Telescope. We've got the Australia Telescope Compact Array up here in Narrabri, and then over here in Western Australia in the outback in Yarrimana, Ilgari, Bundara, which is the Murchison Radio Astronomy Observatory. We have ASCAP. There's also a low frequency telescope managed by led by Curtin, called the Murchison Wide Field Array. And of course, this is where the SKA low is currently being constructed and will be the operational entity for that in Australia. So it's very exciting times. We've got some amazing facilities, and I'll come and show you a little bit with what we do with one of them shortly. But obviously, when I'm dealing with students, we set the scene, relate it back to the curriculum. Most of the curriculum we've identified, students end up having to learn a little bit about the electromagnetic spectrum. So then we focus on what are the properties of radio telescopes and radio waves that make them both unique in some way, but also useful in others. So we talk about the fact that they're longer wavelength, lower frequency, lower energy. But of course, because the radio waves penetrate the atmosphere at the frequencies we're looking at, we can put our facilities on the ground. So radio astronomy data, why would we bother using it in a high school educational setting or undergraduate? Well, firstly, there's lots of it. To put it bluntly, we have more data than anybody else. Our data is publicly available. We currently have about 13 petabytes of data. So, and that's going to dramatically ramp up. So if you want data, we've got lots of it. It's freely available. We've got great managed curated archives. We put a lot of resources into archiving the data and making it accessible. In terms of actually observing, one of the advantages we have with radio astronomy is that we're at least twice as efficient as the average optical astronomer, because we can work day and night and we're not worried about clouds and things like that. So we're a lot more efficient. But no, that means that we can actually observe in real time with a co-located or nearby located facility in a school day. And that can be very useful. The other thing is too, I'll show you some examples of there's, a lot of the technology developments now, it is feasible for schools to have a small radio telescope, and we'll show you a couple of examples of that. But in trying to do radio astronomy at the, high school or undergraduate level, there are very real challenges. And so firstly, it's far less obvious than optical. We have eyes, we look at it, we've seen all those stunning astronomy images. As we've already heard, there are fantastic networks of optical telescopes available for education use that have exceptionally good curricula, well-embedded pedagogy, all of that type of thing. In radio, there are far fewer such programs. There are groups around the world that do it, but there's relatively fewer of us than in the optical domain. Secondly, okay, an image. What's a radio image? How do you interpret it? I mean, if you show people an optical image of a galaxy or stars, people can, relate to it. With radio, it can be a lot harder. Second, if you're actually trying to do science with this, the data formats can be a lot confusing. How do you access it? What does it mean? The software tools, let's face it, they're not necessarily user-friendly. They're primarily Unix, Linux-based. There's not the sort of the options in software that you might have in an optical program by and large. The other thing is, as I've already said, we have large data files. We produce terabytes per hour observing. We've got ASCAP produces huge amounts. SKA low is going to swamp anything else on the planet. So how do we make that relevant, and how are we going to, archive, share that, whatever? Okay, so here's two examples of radio data. So a plot on the left is from a program I run that I'll show you about. It's a pulse profile, but that is some data in a graphical format. The one on the right, I guess, is arguably slightly more familiar to those used to optical. Okay, it's a supernova remnant, but in the radio regime rather than the optical. So both valid. When we deal with students, we give them ideas and we try and unpack what these actually represent, and can talk about color palettes and the like for the image work and so forth. When I introduce students to radio astronomy, it's always really nice to try and do something that's very concrete. And so one of the techniques is this Mark I radio telescope, otherwise known as the cheapest little AM radio you can get. They've got really crappy circuitry, so you just want something cheap and cheerful. And students don't know of this AM band. They don't know radios. Students don't listen to radios anymore, but you show them this and it's handheld, and they can go around and they can literally map the sources of RFI, so they can trace where all the cabling is. They can put it up near the computer screen. They can put it up near a data projector in a classroom, anywhere. So we actually have projects where students can go and map the RF environment in their school area. So that's quite a nice, simple one to do. Now, there are many examples of projects and data online by other institutions that I guess are sort of somewhat familiar to, typical things. So worksheets and the like. So here's one, INAF have produced some great results here. So this is essentially sort of using a numerical allocation to color code a radio image. So that's fairly standard, but, very engaging. These are sort of free downloads. Colleagues at ICRA, so that's the International Centre for Radio Astronomy Research in Western Australia. They produce some nice traditional, I guess, educational resources here for teachers using data from MWA, but in a sort of a traditional sort of worksheet format, but with accompanying presentations, PowerPoints, and for teacher purposes solutions. Makes life easy for teachers. So again, a nice result using real data, but in a somewhat traditional format. Another thing we do have are the idea of sky tours, so introducing students to the facilities themselves. And there's a number of these. So Alma have a walkthrough that you can do online. And there are some other tools, and I'll show you a couple of those. And I've mentioned there too, so Worldwide Telescope, you can do sky tours and pull up the radio data. And Chromoscope from Cardiff is up there, and that's a great resource too. So, for instance, we have our telescope, our facilities out in Western Australia on Inyarimana, Ilgari, Bundara. And there's an online virtual tour that you can do there and go and explore the different facilities. And of course, this is, you know, going to need to be upgraded now that we've got SKA well underway. I mentioned chromoscope, and colleagues at ICFA then, they had a whole sky survey, low frequency survey called GLEAM. And so they had permission to then come up with a variation called GLEAMoscope. So this is quite nice because it's something we can show to, for instance, our Australian students and say, well, this is taken on a telescope here. This is a great, well, chromoscope is fantastic. GLEAMoscope's a nice sort of a variation on it. You can just scroll up and down and see the sky at different wavelengths. Browser-based, nothing to install. So, you know, it's a great little resource to make teachers aware of for when they're covering the electromagnetic spectrum. We've got things, so this is ASCAP. So this is 36 12-meter antennas with phased array feeds. So it's a wide field, fast deep survey telescope. It's we operate it as a national facility. And just before final commissioning, we did what's called rapid all sky continuum survey. So we've got an online version where you can explore it. The dots there are not stars, they're all radio galaxies, so supermassive black holes. But we've identified, you can click on some of the individual images there to zoom in and see what they are. And we just released a new image this afternoon that's, I haven't, because I had to upload the talk yesterday, of a nice sort of a galaxy I can show you later. The other area I think where there's real opportunities is in citizen science. So most of you hopefully are familiar with Galaxy Zoo. And several years ago now, we released a radio Galaxy Zoo, and that used data from our Australia Telescope Compact Array at Narrabri, 6-element antenna. So I was involved in that project, and that was fascinating because it took us a long time to sort of think, how can we get the public to engage and understand radio astronomy data? So they were doing a comparison between the infrared and the radio. And that proved quite successful. There's been a lot of science publications come out of that. More recently, this has just gone live a few weeks ago. This is Radio Galaxy Zoo EMU. EMU stands for Evolutionary Map of the Universe. It is one of the key survey science projects being undertaken with ASCAP. And sort of this was always the intent for our early Radio Galaxy Zoo, that we would learn what worked so that we could adapt it and put it into this version, because with EMU, we're finding 60 million new sources. So we've got a lot of things we want people to look at. So it's early days yet. I'm not directly involved in this one currently, but you know, it's well worth a look and you know, explore it. So we already heard mention this morning of what I think is one of the little game changers. And this comes down to the field of small radio telescopes. So traditionally, there's been, or for many years now, Radio Jove, sort of a decametric, so very low frequency, looking at emission from Jupiter and the like, through the Goddard Space Flight Center. Satellite dishes can readily be used to demonstrate emissions from space. And so the NRAO for many years had the Itty Bitty telescope. And here we can see one that ICRA did with took an old satellite TV dish and put a receiver on there. So there are those examples that are out there, and they've all got, they all work and they're all really good. But I think, as was mentioned this morning, this little dongle about this big, a software-defined radio, is a real game changer. I don't have my one here, but you can plug it in, as we heard, free software, and you can see radio emission, and you can tune it into a radio, or you can look at RFI, you can do all sorts of things with this. So these software-defined radios are a real game changer. Students don't need to try and solder together a receiver and do all that. You can buy these from about $30 up, and we've tested things from $30 to tens of thousands of dollars worth of these things. So we're exploring some of the high-level ones of these for real science projects, but even a $30 one is fantastic for demonstrating radio waves and technologies. So Matt Taylor from SKAO, who was here last week, I think he's up at site today. He has here, and I visited him last year at Jodrell Bank, and he's got what he calls his tabletop radio telescope. It's a nice simple one using an SDR. And you can see here, okay, I don't know why that's not working. Okay, there it is. So this is a slide from that Matt sent me. So it's his slide. But again, you can see the essence of here, of what he's done. You've got a feed horn and the like. Nice bit of kit. I've seen it work and it's fantastic. Great minds think alike. So a colleague of mine developed a thing called LOCUST, the low-cost universal SDR telescope. We had one of an undergraduate student a couple of years ago come and work on this over the summer. She was in the kurigami, which is like origami, but it's cutting and slicing together. So she made the feed horn out of cereal boxes lined with aluminium. We've got a 5-litre lawnmower petrol can below that's got the feed in it. We had it in transit in our headquarters in suburban Sydney, and getting the transit of the Milky Way overhead. So this is a really cheap setup. My colleague Lawrence, who developed this, has had other students do other projects. So we've got a great one that scans for across the spectrum and matches it to the Australian Communication Media Authority, and will identify what each of the things are. It'll say that's channel 7, that's this mobile phone tower, that's this device, and so forth. So there's a lot of good projects there. So it's taken it the next step. So this is Locust. It comes in a little Tupperware pack. We've got a low noise amplifier, an SDR, bits of all the connectors, and a Raspberry Pi, so you can plug it into a computer. Testing it with 3 schools in Sydney at the moment, and with an institution that we collaborate with in Melbourne that I will show you shortly. So it's not a formal, it's a bit like a Skunk Works project at the moment, but I think these things have a lot of potential. And I think the beauty of these is you're not going to get sort of science grade science out of these, but I view them as a sandbox where students actually doing things. So some ideas, like they can build different shaped feed horns, and they can try these types of things to see. And then there's some questions there they can do. Okay, so now I'm going to move on to some programs. I'm going to focus on 2, but I'm just going to point out that there are other projects, some of the long-term running ones, Pulsar Search Collaboratory at NRAO and University of West Virginia. Gavitt, of course, Lewis Educational Centre, using one of the old NASA antennas at Goldstone. And INAF have had projects where they're looking for fast radio bursts. So there are other projects. I'm going to focus on the project that I run. It's called Pulse at Parks. And Pulse at Parks, we started in 2007 and thought it would last for 3 years. And we were still doing our latest session yesterday afternoon on our CSIRO booth. So somehow we're a long-term survivor. Happy to talk why that may or may not be the case. But essentially, this is a free program where we give students hands-on remote observing with an amazing instrument. They studying, observing pulsars in real time, analysing their data, interacting with our astronomers and PhD students. So we've had 260 formal sessions as of yesterday. We've been to about 8 or 9 countries, including we did a tour here to Cape Town back in 2017, and we do it across Australia. Traditionally, they were done as on-site at our headquarters, but with COVID and with the software I was going to show you, we can now deliver these remotely online anywhere in the world, and so we get schools across Australia joining in. So in terms of equity and access, it's significantly improved with the new versions. So the students are analysing it. This is actually at the control desk for Parks in Sydney. All of our telescopes are designed for remote observing. So we use Murrayang, the 64-metre Parkes radio telescope. It is the icon of Australian science. It's on our National Science Register. It's an amazing facility. It opened in October 1961, so it's even older than me just, but unlike me, it's state-of-the-art because it's had regular upgrades. And indeed, in 2 weeks' time, we put a brand new cryogenic phased array feed receiver on it. It's on Wiradjuri land. So the science, the data we take with Pulse at Parkes is fully available for scientists, so it can be used for other programs, and we can see that there. And we have published about 4 dedicated science papers, and the data's been used in quite a few other science papers. The interface we use for students is the exact interface that professional astronomers use. We don't have a dumbed down Mickey Mouse sort of interface. The portal is how we take over control, and we can talk to previous observer and book in on the system. And so here you can see the booking for various days. My project's P595, which is, I think that's me there. And then we have various other feedbacks. We have Frog, which provides visual clues as to what the telescope is doing. So this is a webcam. You can see the telescope where we unpack all this with the students. This would have been a great day because it's early in the morning, the sun's rising just here. The wind is nice and low. And so there's lots of this that we unpack in a session. A typical session is a talk 1 or 2 weeks beforehand, which I can deliver in person or online, and then a 2.5-hour session, of which the 2 hours is telescope time and a half-hour sort of briefing, introduction, and the like. We then have Dargu, and this is how we control the telescope. Dargu is the Wiradjuri word for where to. So this software was developed by our team at Parks. All of this is web-based. There's nothing to install. So that makes it very easy to use, and it's very easy to use. We've got the scheduler, and then we can stream the data down live in a very powerful back-end Medusa. And so here we are in fold mode for pulsars, and we unpack what the different screens here show us. So Medusa back-end, there's normally 5 screens in fold mode. And we can zoom in and see a nice pulse profile, and we talk about what's going on here, what the physics is, and the like. And so we can talk about different properties of pulsars. We've got about 60-odd pulsars in our program that we observe as this. And we actually get some unique science because we can do regular short snapshots of some interesting pulsars that other programs might not sit on as much. So we talk about these are particularly good. These are the intermittent and nulling pulsars that turn on and off. So this was a girls' school 11 years ago, and this thing turned off. And we've literally had I had a student once burst into tears, and I thought they were upset, and they said, no, it's amazing. And this is happening in real time. So this is, I think, the beauty of single dish pulsar astronomy in an educational setting, because you get that immediate feedback. Whereas, interferometry is fantastic, but it's a steeper learning curve, and you're not going to get this sort of immediate results. The other thing is the receiver we use is the ultra wideband low receiver. It's a fantastic receiver. Goes from 700 megahertz to 4020 megahertz. So we've got over 3,000 megahertz of bandwidth. And here we can zoom in, and so we can see all sorts. We talk about RFI and different properties. And we can zoom in, and we can see things like H1. So we've got continuum mode, and we've got fold mode. This is the depressing picture. We can toggle this on or off. We normally leave it toggled off because you can probably guess what they are. They're the satellites. So we have real-time plotting of all the satellites that known satellites might interfere. But again, this becomes an educational point to talk about with students about communication. Everybody likes what satellites give us, but we can talk about the impact they might have on radio astronomy and the like. So here we are talking about the radio frequency interference, and we show them all of that too. The data is publicly available for Pulse at Parks. This is the simplified data that's used in an educational module, but the full data is also available on our data access portal. And so we can see recent sessions there. We've got online module where students go. It's all web-based. They analyze the data, and in doing so, they end up plotting the position of the pulsar on the Milky Way and finding the distance to pulsar, and then they can do it for all the pulsars and start to get an idea of pulsar distribution and the like. We've also been trialing some Jupyter notebooks, so taking it to another level, doing some other science projects, but again, using the real science data and introducing students to programming in a simple, manageable way without them having to install anything. So we tried that. It's quite successful in some of the sessions with more advanced students. So here we can see a plot there. We have had some students use our data and Pulse at Parks data and other stuff for, as Michael mentioned, the science extension course in New South Wales. So these do some pretty high level science. This was one from a few years ago. We've had another one just recently submitted. So these are students in the last year of schooling that have an entire year doing a research project that counts for their matriculation score. Okay, stepping down in size. This is a 3-meter telescope, and this is located 80 kilometres north of Melbourne, where Michael lives. And this is a fantastic program developed by the Victorian Space Science Education Centre. So it's a Department of Education facility, sits in Melbourne, and they do some all amazing programs like Mars mission and all sorts of things. They approached us in 2020 because we've been going down and doing annual Pulse at Parks sessions with them. And they said they wanted to go into radio astronomy. They'd been given a grant, and how could they go about it? And they're thinking about, do we make our own radio telescope? And I said, therein lies pain. However, when I was in Vienna in 2018, I saw this amazing spider radio telescope that was on display and the information. So I said, you need to get in touch with these guys. And they got in touch with these guys, and they got the stand downstairs. And literally a fantastic off-the-shelf turnkey solution. It's fantastic remote control. But then what the VSEC people did, they're experts in curriculum and space. They've got one of their staff has a PhD in radio astronomy. They've developed a fantastic school curriculum that's free for government schools in Victoria. Remote observing with the 3-meter telescope, and they've got the full support with it. So we've been down there, we've been doing pulsar parks with one group, and the other group are doing this online. So, you know, we're at the stage now where this sort of stuff exists. You literally can buy an off-the-shelf solution for very reasonable cost and have an engaging curriculum program with it. So here's an example with it. So I think, you know, there are ways students can engage with radio astronomy. There's lots of different pathways into it now. There are more. I think, you know, some more friendly user tools would be great. We've got all this new data coming out. We want to develop some more programs that utilize that. And then, you know, we're going to have the biggest data sets on the planet. We're pouring billions into these sort of facilities. We want to make sure that there's an educational flow on from that. So I'm very keen to talk with anybody that's doing stuff with radio astronomy and, you know, observations or data, particularly with high school students. Well, I've got lots of ideas, but I'd love to collaborate. So thank you very much.
Thank you, Robert, for sticking to your time and for the next presenter will go straight after and keep your questions. I'm inviting Dr. Mainda. Okay, please, can you come and give us your talk?
I'm Abdulmajid Benida. I belong to the Camden Observatory in Morocco and also at the Kadia University. Okay. So my talk, is it okay? Can you hear me? Yes. So today my talk is titled The Use of Camden Observatory Remote Observing Facility for Training STEM and Education. Well, so it will be in 2 parts. The first one is I developed the factor of development of astronomy in Morocco. And after, how we use the Camden Observatory facility for training STEM and education. And after, I want to show you our acceptation and requirement to create an African network for remote robotic telescope. Well, but before, let me quickly introduce you the case in astronomy, astrophysics in Morocco. So we had especially 4 universities that they teach astrophysics, but mainly we have the only one that have an observatory is in Marrakesh, which called University Kader, and he is monitoring the observatory. So this, I belong to this laboratory, which is called High Energy and Astrophysics Laboratory, which we have 2 groups. The first one for its work about high energy, and the second one astrophysics. Astronomy will make many campaign of observation. And we have also formation for masters for astrophysics for master. And we monitoring the UCA observatory. I call it after UCA observatory. Well, now let us say the factors of development of astronomy in Morocco. I will talk about 3 points. The first one is dynamic around the observatory UCA. And after the second one is the international collaboration project that we lead. And the last one is the capitalization in outreach of international schooling. So let's begin with the first one. No. So our observatory is nestled in the high Atlas mountain of Morocco. I will tell. I will develop this point. And in the course of the last years, the observatory of OCAM then has become a leading of component of the scientific fabric in our university. Why? Because it's good ranking for many discovery from small body, and also its contribution of the field of exoplanet by the famous program TRAPPIST with the University of Liège in Belgium. So now we have many telescopes that operate remotely. I will give some example that we use in education and in STEM. So now, indeed, Duquesne Observatory, okay, have an important point to develop astronomy research and also education in Morocco. So now he's the first platform for scientific research in astronomy, I think we can say in Middle East and Africa, in North Africa. So we have many contributions to scientific research and training, and the observatory play pivotal role in to promote scientific. So actually, additionally, we working to have an reserve dark sky, and we have created a foundation and to have around about 80 kilometers around the observatory, which I think is not so easy to do. So we can see in this map our international cooperation. We have many continents. We have many partners in different countries, in different continents. So they permit that we have collaboration and for education and training and exchange of culture and the early social student. So you can see the observatory and the different projects that we lead. So yeah, we can the main dome is about talk about spectrophotometry of variable star, and this one is the TRAPPIST, which for exoplanet, and we have many from cooperation and Korea, United States, Australia, so many projects. So this become an international spot of astronomy research. Well, so the objective, the main objective of this cooperation, the first one is organizing many observation cooperation in the research. So, also training early career researchers, and finally promoting the scientific method of fostering inclusion in STEM fields. Well, now we have, thanks to the observatory, we have many international collaboration projects that this new with European, for example, and this new project providing mentorship by expert, serving as a direct conduit for collaboration and to achieve gender parity for equal representation of young female scientists. I will tell an example. Yeah, this one, as a saxophone, we have it in between 2017 and 2022. It's called MUNAF with European Union, Erasmus Plus. So it's there for about 5 years, yeah. And we have developed capacity in building for consortium members, create an international opportunity for young African. We have exchange many students to do masters in not only for astrophysics, but science, medicine. So, and finally, implementation and the program of the master and the doctoral degree. After we have make many proposals with the colleague. The first one to European, to have funding from it, and the first, mobility in Africa for training. But this one is especially for astrophysics. So we call it Materna. This one is astronomy, astrophysics cross and across Africa, 5A. And the last one is Afrolink, but Afrolink doesn't have the success, but with the team, we come to have a new proposal. So in this meeting, we have a meeting to try to try to make a new proposal of this. Now, after observatory project, usually in our university and the observatory, we make each year a school by thematic in astrophysics. And this, so we capitalize on this outreach of the school, and we have many students for all Africa and for all students now, also from Europe. You can saw in this picture the last one, yes, will be in June, and the next one it will be in November. It's about topic stellar physics. It will be held in Marrakesh. Look. Okay, now we use the observatory remote facility for training STEM. So as you have seen, we have many telescopes. And I will just describe quickly two examples. The first one is that we use for study of variable stars at the observatory, and we can see more develop for this experience at see the poster of our the student Amrar, the doctorate Amrar, I think by Friday. So you can see the telescope which work remotely. We have a mid 16, and we can get at this. We have two telescopes. The main one is for spectroscopy, and the little one is for photometry. So we can, for the same target, we can have data from photometry and spectroscopy. So we can add the both. Okay, in the bottom you can see the key of spectra that we obtain. Well, so it's the equipment that for spectroscopy we have a spectrograph and many equipment to do the spectroscopy experience. So you can have with Maxim software classical night in screen. So I have video, but I don't know if I have time to show you all the process to have there. So perhaps in Friday. Also we can have spectrophotometric measure. Example, we work on the star RLL, especially RLL. You can see. So this one, the photometry, but we have also to do the spectra of this star. Well, another stars for this one. So we use spectroscopy for this many. We have to do some spectrograph calibration for as you know, for tungsten to equilibrate the flux and to calibrate the wavelength. The calibration of CCD too, to have, and finally, we can obtain this kind of the spectra. Now, how we use this kind of the spectra? So we have two kind of students, high school and graduate student. So for the high school, we basically give them some spectra, and yeah, we know continuum, and show them emission line, absolutely. How can, yeah. So what we learn via the spectroscopy for it's called the temperature, pressure, you know, some, yeah, no, not magnetic field, but basically, you know, as their level permits to do this, yeah, this investigation. So, but for the graduate student, the leads many projects, including the use of the robotics telescope in OKM observatory to observe select stellar objects like variable star or exoplanet or meteor, and the stay, for example, in the observatory for one week, and the leads their project. So you can, in this, yeah, this photo, we have a local student from Morocco, or we can invite from Europe. Yeah, an example for a workshop training in the classroom, how to use the data Kepler test satellite platform, and to compare to our spectra in OKM. As yeah, another example. Another facility, another telescope that we use is called TRAPPIST. Yeah, it is a 60 centimeter telescope. So this used for transit, yeah, exoplanet, and we use yeah, this sorry, this example of telescope TRAPPIST is famous thanks to this discovery, as you know, 7 Earth in 2017 with yeah, with NASA. So we can use this facility TRAPPIST to train a student from European students from like here, for example, from Université de Liège. Yeah, they make there's stay in our authority for 1 week, and yes, they working for a different project. Well, you can hear both Moroccan and Belgium student from Liège after, yeah, after training in the observatory in Camden. So another facility, another facility that we use to develop program STEM is a telescope of pro-arm cooperation. So we use their telescope because they have a very quality image of astrography, and we make yeah, we make a workshop, master class with this, yeah, with this, yeah. Here we can show the many different telescopes from the astronomer and the amateur astronomer. Yeah, this one too. Okay, so as I have said, we use their image quality is for for high school student. He has to have many information from this image. Okay, now uh, we have facility, okay, in observatory, and we want to enlarge this facility to use, and we want to develop a network of remote robotics in Africa. So what is the advantage to do this, yeah, to this network? The first one is accessibility to astronomical and education for more students, and the flexibility and efficiency on observing celestial event, and to have to collect data from all country, and fostering scientific exchange and capacity building, and finally promotion of STEM education in all countries. So what we need as technical requirement for this network. The first one is a robust and reliable telescope, secure and efficient communication system for remote control, advanced software solution for telescope automation, and implementation of quality assurance protocol to answer collect data. Well, and who can help us to do that? For example, potential partnership. So we necessitate to collaborate with various stakeholders like academic institution, research organization, government agency, ministry, international observatory, university, and especially industry partner. Okay, so how can fund or what funding mechanism? So to secure funding, we have to include government grant, research funding, private donation and philanthropic contribution, corporate sponsorship and partnership, and finally, collaboration with international funding. And yeah, we have begun to do that. And actually, we have, thanks to our project with Valerius, with the University of Anvers and Leuven in Belgium, we began to have a prototype robotics telescope facility. And this telescope will be embedded in a large collaboration Africa. We think that about 15 countries in the beginning. So in this one, we don't need many structure. So you can work easily. And we can, with this robotic facility, we also act to protect, to be replicated across Africa. And we and after we did to distribute telescope like this, will very advantage in many countries in Africa. So to conclude, the establishment of this kind of network in Africa, thanks to the facility of observatory of Oakenden, can leverage an existing infrastructure, fostering collaboration among all the country who decide to join us to and securing adequate funding. Now, in April, we have in Marrakesh AFAS meeting. So we observe that we have a dynamical of astronomical activity in our partner in Africa. So we can't use this positive dynamic to create this network, and we have begun, and we have conducted a survey, African Robotics Telescope Network. And we will give you the result and discuss this feedback with you in Friday in the round table. Well, so I think that sorry, I think I think that I have finished. Just just to tell you some advertisements that we have in November in Marrakesh for the first time in Africa. This meeting for variable star, and if you want to come with us, you are welcome. Thank you. Thank you.
Thank you, Melinda, for that sticking to your time. I will go straight to the next presenter, Dr. Edward Gomez. You're welcome.
Oh, no, that is the wrong slide. That's for Thursday. So I have another one that ends in demo. Not that one. Speaking too many times. So this session was intended to be a demo session, and we were imagining that Abdulmajid, Rob, myself, and Daryl were going to demo things live, because nobody likes the nobody likes anything quite as much as doing a live demo, particularly the person doing the demo. And yes, that's it. Perfect. Thank you. What I've done, because it was impossible to broadcast from a laptop at the podium to the screens and to online, I have done a screen record, which I will talk over. And I've sped it up as well in the interests of saving some time. So just to remind you, I'm Edward Gomez and I work for Las Cumbres Observatory. We have these 25 different telescopes, and these are the ones that are for educational purposes, the 40 centimeter class telescopes. If you weren't here earlier, they're arranged at 7 different sites around the world, and the ones highlighted there are the ones that are used for education, these 40 centimeters. And those, but the incredible thing that we have is a robotic brain, Ceral, which schedules efficiently and robotically on LCO. And Ceral means that each class of telescope can operate as a single scientific instrument, where you don't need to pick a telescope and schedule on that telescope. You just say, I want observations of this phenomenon. So thanks to Ceral, we can sort of strip away a lot of the technical obstacles that stand in the way for educational users. So I wanted this to be interactive. So you can, and I know that some of you happen to have computers with you, you can also follow along. So you can log in to first off Kiosk and second the observing portal with those details. Take a picture. You can take a picture of me. For the benefit of those at home, I was posing in front of the slide. You can log in with those details, and I will also do now a screencast of both of those things. And if you've seen that before, I also have a little tease of something coming in the future. So this is going to be, it looks very much like I'm doing this, but I recorded this. So go to kiosk.lco.global and you can type in those details that I just provided. And this is what will happen. So Kiosk is a stripped down, simplistic interface. So you'll see that I'm part of the Project Global Sky Clubs. And you have suggestions. You can choose the moon. You can submit an observation of the moon, a planet, galaxy, star cluster, and nebula. And galaxy, star cluster, and nebula will provide suggestions for different types of object in these different categories. So we could just pick one at random. I'm going to choose M110, and then you click submit, and then it appears on the right-hand side there. You can also do a catalog lookup and choose NGC 891, a personal favorite of mine. And again, you don't get to faff around with exposure times, filters. It just presets all of that for you for people whose Kiosk is their first experience. So I just clicked on Get Image on one of the ones that I've observed before. And I'm going to do another one which has 3 separate observations in RGB, and it generates these images on the fly. An RGB observation and a beautiful full color. So that's M20 there. Very simple interface. So this is, if you want to then go from there to more advanced things, then you can put in your username and password here and observe.lco.global and experience the full power of the observing interface. But you'll see that each one of those observations I just made has an entry in this observing portal. And you can see what behind the scenes happened to put that in. And within seconds, that observation had been scheduled for observation at our Canary Islands site there. And you can see this is a visibility curve, and then on that tab, the data will be available. So I'll look now at one that's already been observed, my picture of M101. You can see all the details again, the exposure time that was used. But now on the data tab, you can see a thumbnail. If you click on the thumbnail, it loads up a full-size image at the full resolution. You can also download the data right from there. It shows you the exposure time and the filter that was used. There you go. You've got 2 different sorts. You've got the raw and the reduced, and you probably always want the reduced. But if you want to actually do the observation in there yourself, give a name to your request. You choose your project. There are some other criteria there which you can select, but the most important thing is your target name, which the system will look up for you. It's desperate to put my name in there. And select an exposure time and a filter, and you can reproduce what we had before. It also tells you there are 2,294 images of that in the archive. And there you go, there's a visibility, so you can see that your object is visible at the current time by several of our telescopes. You can also do more complex things, like the system will automatically generate a mosaic for you here. So with multiple pointings that you can configure, you can see that it's off center. So I'll just cancel that and reselect as a center option at the bottom there. I'll say true, and it'll regenerate the mosaic. It's for the target I've chosen, a mosaic isn't entirely appropriate, but for larger targets, you can imagine that it would be. So as well as other parameters there, you can select. This is for sidereal targets. We can choose non-sidereal targets. I'm just going to clear that form and start again. So enter the details, my demo, select the proposal, the project ID, non-sidereal. I'm only part of one project on this. So now we're going to change sidereal to non-sidereal, and I'm going to change that to major planet and add the planet Mars in there. And it'll look up the orbital elements to save you the job of doing that. And I'll add an exposure time and a filter. And then we'll be good to go. We'll just choose anything, H alpha. And you see on the right-hand side, green ticks mean that everything's good. And we could submit that for observation within the next 24 hours. And you can also choose minor planets and comets. If you select minor planet and try and put in, as I do now, comet, then you won't, Pons Brooks, then you won't get anything. So there you go, 12P, which is the other identifier for Pons Brooks. And you can see that Pons Brooks is never visible within those constraints. I think it's very low in the sky, so we probably have to adjust the air mass. And that's a really whirlwind tour, but hopefully you can have a little look around there at some of the, and this is one of the other images that I showed you in the kiosk interface. So the color image there, and you can get all the data from there. And there's a handy link to the archive. And so you can click on that and download the data from the archive, but you can also search the archive without being logged in because it's open source. Every observation is public access after 12 months, and education images are public access immediately. So you can search for data, change the time, and see that. But there's something you'll notice there at the top that says LCO real-time test. Now, in the near future, we're going to be launching a new project called Photon Ranch that Michael Fitzgerald has been working on for quite a while now. We're working on together. And this will allow you to use the telescopes in real time. And for education, we'll have a more unified real-time and Q-scheduled interface. It's still being worked on now, and here is a tease of it. So there's a planetarium view, and there's an Aladdin preview up in the corner of what we want. And I'm gonna, if I press that, oh yes, you can select an exposure time and filter as before. But now the telescope will move at your command instead of it being asynchronous. You'll have the option of doing both, and you get some feedback there of the site being available, the telescope's tracking, the camera's exposing. I've sped this up, as you can tell. And then the target was downloaded. And that was a tease, and my time's now out. So thank you very much.
Thank you for that presentation, very brisk and to the point. Yeah, having gained some little seconds now, let us go to the next presenter. So at the end, we can all interact with them. Let me call on Dr.
Boroska, if I got the name right. It's a turn now.
You. So today I'm happy to give you some introduction about what so-called iRobotic telescope network and their application to education, outreach, and research. You know that in Southeast Asia, in Thailand, we established the National Astronomical Research Institute of Thailand, or NARIT. Yeah, we have the headquarters we call Princess Sirinthorn Astro Park over there. And we have two national facilities in astronomy. The first one is 2.4 meter Thai National Telescope, the TNT. And also this just finished installation, TNRT 40 meter radio telescope in Thailand. Apart from the two national facilities, we also have 5 public observatory all across Thailand. And also today I want to focus on the iRobotic telescope network outside Thailand in 4 countries, in Australia, in Chile, in China, and in United States. We have 4 robotic telescopes I want to focus. So this allow us to make the observation for almost 24 hours, day and night, and also in the northern and the southern hemisphere. This is the 4 site in Chile, CTIO, at CTIO, China at Gaomeigu Observatory in southern China, in United States, the Sierra Remote Observatory in California, and in Australia, the Springbok Telescope. We have 4 Thai robotic telescope network. And this is the specification of the TRT, just the 0.7 meter CDK telescope with the Andor CCD camera, and also the set of wide and intermediate band filters for photometry, and also the RGB filter bands for astrophotography. This is the sample of the images from the TRT. It's very nice pictures. And this is the number of hours used on the TRT. Yeah, CTIO, GMO, SRO, and SPO. Yeah, you notice that in 2020, actually the one at CTIO is a 0.6 meter telescope, but we plan to replace to the 0.7 meter telescope. So, but that time it was the COVID-19 pandemic. So the installation of the 0.7 meter at the CTIO was delayed until 2023. So this year completely operated the 4 robotic telescope. In the Southeast Asia, we have the Southeast Asia Astronomy Network. Actually, we want to promote astronomy not only in Thailand, but also in the region, in the Southeast Asia. So we promote successfully, the education, outreach, and research in astronomy for driving the deep learning, the technology development, and also the human capacity building. So we have the teacher training program in Thailand. We provide this not only for Thailand, but also in the Southeast Asia. We have the basic level, intermediate level, and advanced level. So in the advanced teacher training, the teacher and the student, they have the opportunity to access our robotic telescope network. Yeah. So they can use the robotic telescope network for their research project for advanced teacher training. And this one just the summary report of the telescope, of the robotic telescope, yeah, at the SPO in Australia. So you see that the number of the image taking, the calibration taking, and also the total observing time compared to the CTIO. Yeah, you see the observing time is double due to the good atmosphere in CTIO. Yeah. So welcome to join our TRT network. And actually, the robotic telescope is the telescope. They just carry out the observation, just carry out by the telescope without the operation directly by the principal investigator. So you're welcome to join our TRT network, just creating the user account. So just sign up and log in. After get the approval of the user account, then what you have to do is to create the proposal and submit the proposal to the TRT. We have the time allocation committee to consider and approve and give the priority to the research project. So after that, you just simply make the observation request, and then you can wait for the result. Yeah, this is the observation log. Just showed the name of the PI, affiliation, the number of images taking, the project ID, and the title. And this is another observation log where you can see the object ID, the target, the number of images, exposure time, priority, the proposal number, and the name of the PI. So just welcome to use our TRT. Thank you very much.
Yes, thank you, Dr. Brunska, for that presentation. Let's go to the last presentation of the evening before we have our little discussion and questions. Let me invite Dr. Dare Jansen.
All right, thanks. So May gave an overview of Skynet earlier and some of the tools, and my talk is actually going to be more focused on one of the projects that we've been working on developing, and this has been happening for several years now. Basically, Michael and Dave McKinnon and Saeed Salampur started working on this, and it sort of morphed into a Skynet-y project, and then I sort of took over leading developing things with it a couple of years ago. And yeah, and so this project sort of touches on the question that Edward asked earlier about whether our goal is with robotic telescopes and teaching with robotic telescopes is to make it so that students can access robotic telescopes to collect data, or if we should be, you know, aiming to move them more towards science. And this is actually a project where not only are students able to learn by doing astronomy, but actually even learn while contributing to astronomy. So there are a few different pieces to this. Skynet Afterglow, which May started talking about, and then this Astromancer tool that we've she showed that we have some tools that we've been working on. This is one of them, and then this updatable catalog Astronomicon. Okay, so basically my talk is two parts, talking about the image processing and an HR diagram analysis tool. Afterglow access is accessed at that top site. There's also another website that's a little bit easier to access. Doesn't have quite all the bells and whistles, but Tim Spuck worked on developing that. So there are lots of features in Afterglow that students can use to analyze their images. So you've collected some images, just flip the ability in a web app to flip through and inspect them. We have this cosmetic correction tool where with a click you can clean up an image. There's rerun astrometric calibration, or if that's not been done. So source extraction and WCS on an image with a click. Aligning images via WCS, or there are several other alignment tools, options available in there, and they're all sort of like one-click things. Stacking images, so you can select a bunch of images, and once you've aligned them, you can stack them up. And so there's the B image and the V and the R and the I. This is M46 that I've got some data. Group the stacked images together and colorize each of the layers and then make a color image. But once you've sort of default color settings, you can see on the image histogram there that right here that things aren't exactly lined up. So we want to correct that and get the color balances right. And so there's a tool in there to just automatically calibrate the colors based on the magnitudes of the stars. So using 0-point calibration. And there's even the ability to de-redden images. So if you know what the reddening of the, say, the star cluster like this is, you can de-redden them and see what sort of the natural colors of the stars are. And then adjusting the image contrast to make a nicer, clearer image. And so there's my image of M46 with this planetary nebula, and then there it's de-reddened. You can really see the difference. It's a little bit, that's a little redder. It gets a little bit bluer when I click. Anyway, so lots of these one-click image processing features, cosmetic correction, and all of that. And then there's also batch photometry, so auto source extract from the field and then run batch photometry on all of your images or whichever ones you want to photometer. And that brings me to the next thing, this Astromancer tool. So we have the ability in here to either upload data, just dropping a file taken from Afterglow, put it in here, or if you don't have a data file and you just want to go and analyze a cluster, we've got a backend catalog that has Gaia and 2MASS and some other catalogs. So when a photometric data file is uploaded, we can right away the data upload cross matches to Gaia astrometry. So we've got not just the photometric data, but also all the astrometric data for each of the stars that you photometered in your images. Or our backend catalog has Gaia, APAS, 2MASS, and WISE photometry all pre-matched to Gaia astrometry for doing cluster analysis. And there is a 5,000 source limit, so you're only allowed to load in 5,000 stars because it's sort of the analysis tool just doesn't do very well. It's a web app if there are more sources than that. Anyway, so yesterday I looked up M67 and found that I had to limit my radius to 0.5 degrees in order to keep under the 5,000 star limit to begin with. And this is a to begin with thing. We can get all the stars in a cluster eventually up to 5,000. And then moving on from there to the next page here, we have all of the proper motion data for this cluster, or for this field, I should say, on the top here. So histograms for right ascension, proper motion and proper motion in declination, and then a 2D proper motion plot. And so you can see the cluster is moving relative to the Milky Way stars there. And then here's the color magnitude diagram. You can see there are a bunch of field stars in there in addition to the main sequence distances. And just this is sort of junk placeholder. Anyway, and so here I've narrowed in on the stars in the cluster in proper motion and in distance. And you can see the color magnitude diagram pops out, and I chose this one because it's really fun. Can zoom in on them. That's what these two toggles up top here and here do. So I've zoomed in on the histograms just to sort of narrow it down. And so these are all the cluster stars, including all of these things and all of this and whatever. So it's a very interesting cluster. Once we've determined or set the proper motion ranges and the distance ranges, then we can widen our search radius and pull in more data because we'll stay under the 5,000 star limit. And so the next step in this tool is to go to the archive fetching. And so we can pull in all of the Gaia data and the APAS and the 2MASS and the WISE so that we can analyze everything. So that's what I've done there, pulled it in. And so there's a whole bunch of field stars in the region, and we don't pull those in. We just grab the stars in the cluster, and I think there was 1,641 in this cluster. Turns out with the ranges that I had set. So then just going back to this step to have a look at the different histograms, it looks like I've got decent ranges, and you can see a nice color magnitude diagram for the cluster. And with all of these interesting features in it, the red giant branch and all of that stuff. There are all these unresolved binaries in M67, so they're brighter than and either the same color or maybe a little less red. White dwarfs down over here, blue stragglers and stuff. So we want to fit an isochrone. We want to fit an isochrone model to this to determine the cluster's age and its metallicity and all those things. So that's on this next step. So in this step, we can adjust the parameters and we just build our HR diagram. So here I did a Gaia plot. You can toggle between color magnitude diagram or HR diagram, which is absolute magnitude and intrinsic color with the reddening taken into account. And I've sort of determined the age, metallicity, and all of that for the cluster. Can add up to 4 in the different filters, even mix and match. So there's W1 versus G prime minus R. Anyway, and look at how those catalogs work together. And then there's a results summary where we're calculating a bunch of interesting things on the back end, like the velocity dispersion, because we've got proper motion data for everything, and the mass and the size of the cluster, which is just a half-light radius. Yeah, so we've done that, and then students work with this stuff. This is actually old results from last winter term, but just sort of highlighting some of the things that this student pointed out, the fact that they were able to observe a cluster at negative 58 degrees declination from Saskatoon, which is really cool to them. And then also, oh yeah, and then the reddened versus de-reddened image, and then also their values for their isochrone versus the values that are published in the Milky Way star clusters catalog. So this first year student, university student, being like, hey, I did a better job than the pros. So which led us to build this thing, this Astronomicon thing, where, if we're running into a bunch of this stuff, we want to be able to update our catalogs, because every time we start working with real data, we seem to find that the astronomical catalogs are a big mess and everything isn't perfect and everything needs work. So why not let our students work on it? So we built a catalog site that can be submitted to from this last page, and click that button, brings to a Google sign-in. And then here's my revision, and this thing is a real first version, lots to be done, but I have to build a color magnitude diagram for in order for a value to be calculated. And what it does is right now, all we're doing is just calculating the shortest distance from all stars to the nearest point on the isochrone. And here, this student did a better job than I did at that smallest distance, sum of distances. And so that's in the catalog. And so we've got this catalog here, and all of the ones, she's not rounding when Mandy built this, she's not rounding the radius. So you can see anything that has large numbers, that's values that students have submitted. So they're already starting to populate this catalog with updated values from just the last couple of terms of classes. So yeah, that's where we're at. We've got lots of plans, lots going on for next steps, and moving on to variable stars and whatever, but we're pretty happy with that tool and how it works in the classes. And there's just a bunch of people who've helped on this project over the years.
Thank you very much for the presentation. I think with that, we can say we have our last presentation today. We're going to now go to the roundtable. Please, can we clap for those presenters who are presenting for this session? No, I did not hear that. That should sound like astronomical clap. So I want astronomical clap. Clap loud for them, please. Yes, we are building our lexicon these days from this conference, this GA. There's Astromancer and Astronomicon. That's new one. I'll add to my dictionary for that. All right, please, all the presenters, can you just move the high table there? And there's from there, the mic. All right, as it is now, they are there. We can see these gentlemen. It's time for us to actually make contributions or ask them questions. You can remember the presentation from who is listening to the radio to the last one. So let us discuss with them and agree. Okay. All right, somebody's already holding the mic there.
Thank you, gentlemen. Very informative. I have a question from the gentleman from CSIRO. Do you have any sense of the number of high school students going into universities who take up astronomy and branch off into radio versus optical? Using Australia as an example.
Simple answer is no from our program. Doing longitudinal studies like that is one of the hardest educational research, and there's all the privacy. And for most students, it's a one-off experience. We have had 2 students who have self-identified whilst doing PhDs that taking part in Pulsar Parks was the initial trigger that got them in. So one now works at ICRA as a postdoc. The other one, I don't think she was in radio, but she certainly got into astronomy because of that. That's not the purpose of the program. We don't want thousands of astronomers, professional astronomers coming out of the program to be realistic. It's really we're using radio astronomy and pulsar observations as the context for engaging them about science and the processes of science, and seeing science in action. And one of the things that does come out from our program is, as the answer when they ask lots of questions about pulsars, is we generally say we don't know, and that's why we're studying them. And that's been a transformational moment for some students, because what do you mean you don't know? That's not what they're used to thinking about science. I think science is what's in the textbook and what's right, whereas we're showing them how we go about trying to figure out all these things that we don't know about.
Right. Yeah, to the front here.
Thank you. My question is for Dr. Jansen. I do not know for how many filters you have been computing the tracks to be fit on an open cluster. But for example, if I take two observations at different filters taken by LCO. Can I download it? And then what about the filters used? For how many filters have you computed the evolutionary tracks?
Yeah, so the isochrone models that are on in the tool, they're parsec models, and yeah, they work with all of the filters, like anything, all of your optical filters, and also with the infrared and everything. Everything is being computed, so that it doesn't matter.
It should be, yes, all the classical filters. I mean, something like that. Yeah. Okay. Okay. Thank you very much.
All right. Thank you. Another question or comment from anywhere? Okay.
I have two questions actually. So the first is for Edward. I really like the kiosk. Is there any like mechanism or plan to have something that kind of takes you to the next step of like, okay, I've done my first observation, and now what did that do?
Yeah, thanks for asking that. So the actually a lot of the tools for education are being revamped currently. So kiosk is something that is going to be supported for a while, but you're right, there is a big jump between that interface and the second one that I showed, which is a full-on, and it requires educational scaffolding. You have to have, you know, some training, some knowledge transfer in order to get you from one to the other. And that's something that Michael and I are working on, providing a course. And also I'm working with LCO software people to have an observing interface that does bridge that gap more. And that was the little tease that I showed you at the end. There's much more of that, but it was only a tease.
Thank you. My other question is for Rob. Is there any like desire or intent to take the low cost telescopes and kind of disperse those to more than just a couple of schools?
Well, at the moment, it's a bit of a small level project. It's not even an official project. We haven't got a definite plan as to the next stages yet, basically because we're also busy doing our other things. One, whether we look at basically buying so many sets of the kits and making it available for schools. The other option is most of that stuff can be readily available online. So literally just putting the shopping list with a link to Amazon or whatever, where people can buy it, and providing the materials and the software available for download. Some of that can be problematic just in terms of software licenses and things. So we're a government organisation. We have to be very careful that obviously we're fully compliant with all of that type of thing. We'd certainly like to get it out more. The feedback we're getting from schools is very encouraging, and I think it's got a lot of possibilities. So I certainly want to see it go further. We just don't know exactly the best way to do that yet.
Yes.
Hi. My question is for Edward. You briefly mentioned Photon Ranch coming up. I'm just wondering if there's a estimated time when that would go live, and whenever that happens, would it also be kind of publicly available like the rest of the LCO stuff?
Yeah, thanks. So yes, I showed Photon Ranch without any explanation at all, quite deliberately. So Photon Ranch is a kind of a new endeavor for LCO. I won't go into the historical origins, but there will be several different components, and we're still working out the details of those. But the Photon Ranch software, the control interface, and the educational resources to go along with that will hopefully be released in the second quarter of next year, and they will be running on the observing software will be running on our current 40 centimeter telescopes. There will be additional telescopes as well, and the idea is to offer them freely for educational use. There is another side plan to allow the photon range software to be run on amateur telescopes, ones that are in fixed observatories. But the details of that are still being worked out quite a lot, but there's been a lot of effort put in to the software development, that a lot of which Michael has done to make that software run. And if Andrew's here, Andrew has, Andrew's has a photon range or a telescope that's running photon range software at his school. So yeah, we're working our way through it at the moment, but it will be free.
All right, thank you. We have two questions from the online participants. I have one from William. William, can you unmute and ask your question? Can you hear us, William?
Okay, I'm unmuted. Sure. This is to Abdel Majid Benhida, Edward Gomez, and Boomruxar S. You have pursued purely remote robotic observing capabilities. How would you compare this mode with remote hosted observing, whereby users can communicate live with the on-site hosts?
So, yeah. Can you repeat your question? I don't have, yeah.
Okay, sure.
Yeah. How?
To Abdel Majid, Edward, and Ruxar, you have pursued purely remote robotic observing capabilities, which are extensive and powerful. How would you compare this mode with remote hosted observing, whereby the users can communicate live with the on-site hosts?
Yeah, so in that case, so you're imagining an observatory with a controller inside, and the people talk to the controller inside the observatory dome. So I have no experience of that at all.
How made the
if we've had a comparison of those two.
Yeah, thank you. So I can describe how we made our observation with students. So we have access directly to the in the classroom, mainly for graduate student, to the remote telescope, and we show them all the steps that we need to observe, and after we have the data, the data, and after by one day, what we do is we can how to analyze the data and give to give them to analyze if basically if they are graduate student, and after we discuss. I think that what I'm understanding from the question, how to describe our process to robotic telescope when we have in Oakland. But after, mainly in the other case, we have data already, and with the high school, we only show them the data, and yes, because we can make observation with high school in the night. So we have to the place to the high school and show them the result that we have. I hope that I answered to your question. No. So, I don't think this way.
I think you came close. What I
All
have
right,
in mind is working with high school students.
I'm Budraksa from Thailand. Yeah, as I already mentioned in my talk, the advantage of the robotic telescope allow us to make the observation nearly almost 24 hours. Yeah, both in northern and southern hemisphere. We have several telescope which we are not classified as the robotic telescope. But we have the limitation of the atmospheric conditions sometimes. So in using the robotic telescope, I think we can disseminate the opportunity for school, for university to use the telescope. We have more opportunity to access the telescope, and we have more observing time for using the robotic telescope. Yep.
Thank you.
All right, guys, another question from online. Maria is asking this question to Dari Johnson. Maria, can you unmute and then ask your question?
Yes, thank you. So, hi, Daryl. I was amazed by the tools you presented. And my question, maybe I missed that part, but are those tools going to be accessed openly, or they are only available to Skynet users?
Yeah, okay. So the Astromancer tool is just available through the web link. There were a bunch of links in my talk, and if you saw down at the bottom, I had a tiny URL .com/IAU 2024-Janssen. Anyway, and that's just a link to my talk, and all of those links are in there. So if you just want to email me, d.j@usask.ca. The tools are accessible by anyone. The one tool that isn't is Afterglow, in the way that you can access Skynet observations. But the second link for Afterglow that I gave, that Tim Spuck developed, and that they got online, that one is just a Google login. But then the Astromancer and Astronomicon are all just web links and web tools that are openly accessible. Thanks
Thank
for the
you.
question.
Yeah. Any other question from in the house? Okay, Michelle.
Thank you. My question is for Abdelmajid. You show us a drawing of a future remote robotic telescope that you would like to install in many, many places. So have you plans where to set it up? That's the first. Will it be, how will it be run? Locally by someone who sign a MOU between some organizations that you will create and this place where the telescope is taking place? Who will take care of the telescope after it has been installed? And how it will it be costly for someone wanting to use the telescope? How the applications will be done later on when the project will be on.
Thank you. Thank you, Michel. So in the beginning, the idea, we have many colleagues from Belgium and France, and some colleague who in the team from EA, from which contribute some project before, and we have the idea to work with them to make this project. So now in the size of this project, in the first telescope will be placed in the observatory of Camden. So in Camden, we have no problem. We have internet. We have someone if we need to access. So we have electricity. We have internet. So we don't have. So we can when you visit in observatory Camden, I think that we will have, and with colleagues, all the problem that all the facility that we need that it work normally. So after, when I think the first year, and after we will fabricate other telescope, and with other colleagues, I think that it's depend each country have facility or not. But I think in the goal is to check the country who has any facility, you know. So I think that if you have electricity, internet, and if you I think that you don't need someone who is being 24 hours in 24, which it's a little structure. So we need maintenance, sure, but I think that the objective that say a little to make a little observatory with few how to say with few equipment. So we need. I want to tell you about it's about we cost about 40k euro. So and the next phase is to reach for some partnership to finance for countries that we need. I think that after we have Burkina Faso, Senegal with Selma, we have cooperation, and I think the first country, the next country that we can change is Senegal and Burkina Faso. That we have some colleague that we have happy to work with us. Yes, I hope that. Thank you.
Thank you, Hinda, for that. I think we have almost exhausted our time, and there's no other hand that's raised up for questions, both online and in-house. So with that, can we give a round of applause to the presenters, the discussants? Yeah, let me call on Michelle to give us a round of. Thank you, Michelle.
I would like because I must tell you that we plan carefully that all this design, the connection directly for the connection directly to the telescope and real observations, and maybe to have a look on in 2 days on the 15th on the observations. But unfortunately, we happened a short time before the GA that it would not be possible at all. So our deepest thanks, and by our, I mean all the SOC of the focus meeting, to the speaker of this afternoon for having changed their presentation. Thank you very much.
Thank you. Please wish you a happy evening and enjoy yourself and relax. Yeah.